Maybe shall we try the title slide? So
Shall I share it?
yeah.
Because once I share, I won't unshare it. The title is not that thing. Title is a video. So that's why I'm telling waiting.
Okay.
So let me share it. Shall I share it? Yeah. Because once I share, Hello?
Yeah, yes. Audible.
Audible, okay?
Yeah.
Is it visible?
Yes, visible, full screen. Yeah.
Good. Now, how to remove this side one?
No, that's YouTube full screen, not possible.
Yeah, but I need to off my video. Is that possible? Let me stop sharing first.
Okay.
Then off the video. Okay, now share again. Can you see my?
Yeah.
Can you see my slide?
Yeah, Star Trek, New Generation.
Yes.
Yes.
And you can hear clearly, right?
Yeah.
Okay, that's great. There's no picture now in the site. Can you see the full screen?
Yes, full screen. It's full screen.
Okay, great. Okay, now I will wait till the chair asks me to start.
Yeah.
Yeah, let's wait for 3-4 minutes. Okay, so we have 1 minute. In that minute, I will make some announcement. So let us start the day. So today we will have one lecture on exoplanets and one lecture on instrumentation. And before the lecture starts, I want to give two announcements. The first is that the tutorial and lectures page on the summer school web page, we are uploading the materials at the end of every lecture or as the tutorial material comes to us. So you can keep watching that space. And for today's tutorial, there is some material which you can download. Please go and look at that web page. Then the second thing is about questions. So I think today the first speaker, Professor Sujan Sengupta, who will lecture on exoplanets, he prefers questions at the end. So please type your questions as the lecture goes along in the chat box, and we will come to it at the end. But please make the questions relevant. Don't make them too long. And importantly, don't clog the chat box with irrelevant questions which are not relevant to the lecture. Okay, so I think we can start. It's already time. So Susan, over to you.
Yeah, thank you, Prabha, and good morning to everybody. I'm not sure whether it is summer, autumn, or a rainy season, but I'm always fascinated by a school, not for appearing in a class, but for storytelling. So today, instead of taking a class, I'm going to tell you a story. So please fasten your seat belt and have your earphone. We are going to space.
Space, the final frontier. These are the voyages of the Starship Enterprise. Its continuing mission to explore strange new worlds, to seek out new life and new civilizations, to boldly go where no one has gone before.
To explore strange new world, to seek out new life, new civilization. That science fiction originated by the imagination of human and based on the extrapolation of contemporary knowledge. Today, I am going to tell you about the systematic and scientific effort of astrophysicists with a purpose to explore new strange world, to seek out life beyond the earth, civilization beyond the solar system, which aims to answer the eternal question of mankind. Is anybody out there, or are we alone? Now we know one planet, but certainly which harbors life, which is habitating. 5,000 years ago, the Sumerian, they imagined that their civilization, their arts, their technology, all are taught to them by intelligent alien life from outer space. The Babylonian also thought that the stars and those lights in the sky, they are the place for god and goddesses. Even the Greek also considered that moon is the place for god and goddesses and for the departed soul. And thus the imagination that intelligent life or alien life exists outside the earth is an eternal, is a very old one. And that's why this question has become eternal. But about 2,500 years ago, this plurality of life was destroyed by the proposal or by the suggestion of the Greek philosopher Aristotle, and around about 1,000 years after by Ptolemy. So what they suggested that Earth is a special place which is the center of the universe, and all the planets and the stars and all the lights are orbiting this place, the Earth, and so there will be no possibility of life anywhere. Earth is the only place in the universe based with life. And this philosophy was adopted by the Catholic Church in Rome, and they made a rule that nobody should oppose this view, and if they oppose it, it will be a kind of sedition or something like that, and he will be punished. So people at that time, like Aristocles, realized that there is a problem with the Aristotelian theory, but their voice was completely suppressed. Finally, in 16th century, the Polish astronomer Copernicus came up with a theory which is completely opposite to the Aristotelian philosophy, where he told that it's not the Earth, it is the Sun which is the center of the planet of our world, and not only the planets, he predicted all the lights, that is, all the stars are also orbiting around the sun. This was supported by Giordano Bruno, and he was punished. He was burned alive in the street of Rome. But then the Italian astronomer, the Tycho Brahe, he collected large amount of astronomical data. So with the use of this data, he realized that the Aristotelian philosophy is not fitting the bill. So, however, he came into a compromising theory. What he told that the stars and the planets are orbiting the sun, but the sun itself is orbiting the earth. So in this way, this is a peculiar mixture of geocentric or earth-centric world. Once Tycho Brahe passed away, his entire data was obtained by Johannes Kepler. So then he realized that Tycho Brahe was also not right, and it is Kepler, it is Copernicus who was right. So Kepler then discovered the three laws of the motion of the planets. Then came Galileo Galilei, who for the first time used the telescope and then discovered the craters of the moon, discovered the moon of the Jupiters, and he strongly advocated the Copernicus theory that Earth is not the center, it is sun which is the center. In fact, it is Giordano Bruno who realized that if sun is a star and if the planets are orbiting it, then the millions and billions of lights in the night sky are also like sun. If that is the case, then these two should have a planet around them. If they have planet around them, then definitely some of the planets are very similar to Earth. And if there could be Earth-like planet, then there could be life also in some of the places. So the search for planet outside the solar system started. But during this 16th century to 17th century, the astronomers were busy in discovering the solar planets, the new planets beyond the Saturn. Up to the Saturn, this planet was known by the ancient people. Then Uranus, Neptune, and finally in 1930, Pluto was discovered. At that time, there was some effort of discovering planets outside the solar system, but all was in vain, all was false positive, that is, nothing has come up. Finally, the first official report of the possible discovery of exoplanet came from Madras Observatory, which was functional during 1786 to 1899. And after 1899, this Madras Observatory was shifted to Kodaikanal Solar Observatory at Kodaikanal, which traced back to the Indian Institute of Astrophysics and got its center at Bangalore in 1971. And so this year we are celebrating the 50th anniversary of Indian Institute of Astrophysics, which actually originated from Madras Observatory. And in 1855, the then director of Madras Observatory, Captain William Stephen Jacob, so he did some astrometrical calculation of a binary star called 5070 Ophiuchi. What Captain Jacob noticed by taking the position of this binary, two stars in the binary, that they are not exactly following Mr. Kepler or the Kepler's law. So he suggested that if a Jupiter-sized planet is orbiting as a third body in this system, then this anomaly in the motion can be explained. This was supported by the astronomer C in Chicago Observatory And then even after 50 years, this was supported by other people. But as more and more larger telescope appeared, as more and more technology of camera or photography or image processing appeared, it was found that Captain William Stephen Jacob did some mistake in his calculation, as he missed the contamination by the Earth atmosphere. At that time, more than 150 years ago, he did all the calculation by hand. There was not computer, not even calculator. Nevertheless, this report, which was published in monthly notices of the Royal Astronomical Society, is currently considered by NASA and by ESO that the first false alarm for exoplanet. So after 1855, several people searched for planet outside the solar system, but all the results turn out to be false alarm. Finally, in 1995, this gentleman, Michel Mayor of Geneva Observatory, along with his students, Didier Pouillot, reported the discovery of an extrasolar planet around a solar type of star 51 Pegasi in the constellation Pegasus. And for that, in 2019, they were, after 25 years, they were awarded the Nobel Prize for Physics. Now, if you see by a moderate or a small telescope or a binocular, 51 Pegasi is just 50 light years away from us. So it's a bright star, slightly bigger than the sun, but you can see it as a dot. And we know that the planets don't have their own light. And even if they have their own light or the reflected light, they are hidden by the immense brightness of their star. So how Michel and Didier discovered it? So these exoplanets are discovered by indirect method, by their impact, by their effect on their stars. So the method that Didier and Mayor Michel and Didier followed is known as radial velocity method or Doppler method, which was suggested by Otto Struve some 40 years ago in the journal Observatory. So what is this radial velocity method? Now, when two celestial body orbits around each other, they don't orbit around any of the component centers. They orbit around around a point which is called the barycenter of this object. Now, if the mass of these two objects are same, then the barycenter lies exactly at the center, joining the centers of the two objects. Now, if one of the object is heavier, then this barycenter moves towards the center of the heavier object. So, if there is a planet and there is a star, then this barycenter through which this object rotates are inside the heavier object or the star, but not exactly at the center of the star. As a consequence, the stars wobbles due to the presence of the planet. Now, if the planet is orbiting edge on, that is at the 90-degree inclination angle, then one can see there is a radial velocity to and fro. The star is coming towards you and is going away with you. This is the radial velocity of the star due to the planet. Now we know very well that our Jupiter imparts about 12.4 meters per second radial velocity, and the Earth also imparts tiny radial velocity, that is 10 centimeters per second to the sun. Now, because of this radial velocity, the to and fro motion of the star, the wavelength, the light that is coming from the stars, its wavelength also gets shifted due to Doppler effect. So how the astronomer measures this tiny motion of the star due to the planet? Now they send this star light through an instrument called spectrograph, and that splits the light into several colors, and this spectrograph contains some vertical black line which are due to the absorption of light by the element present in the outer layer of the atmosphere of the stars. Now, if the star is fixed, then these lines are fixed corresponding to particular wavelength. It depends on the nature of the element, what type of element is there, and their associated wavelength. But if the stars have slight movement, then these lines moves towards blue and towards light periodically. Now, from this periodic movement of some particular line, for Mayor and DDR, they picked out a iodine line and watched the movement, the to and fro movement towards the blue and towards the red of this iodine line, and then they confirmed the presence of the planet 51 Pegasi B. This was immediately within 1 month was confirmed by Mr. Mayor of the American group, and that's why it got the credit of the first confirmed exoplanet. Otherwise, a planetary object was discovered just in 1992, but not around a normal star. It was around a neutron star or pulsar, but that was confirmed as a planet much after 1995. And that's why 51 Pegasi b is still considered as the first confirmed exoplanet orbiting around a sun-like star. Now, apart from this radial velocity method, there is another very popular method which is known as transit method. This was also suggested by Otto Stuck in the same paper in the journal Observatory in October 1952. So what it says that when a giant planet orbits very near to its stars, then some part of the starlight is blocked by the shadow of the planet. So it's just like the way you see the transit of Venus, you see a spot traveling across the disk of the sun. So the light, the brightness, nevertheless falls by a fraction, by a very tiny fraction. But if the planet is sufficiently bigger, suppose if a Jupiter-sized planets and which is even nearer to Mercury orbits around Sun, then there is a large amount of drop will be there in the flux of the Sun. So similarly, if a giant planet, Jupiter type of planet, or even a Neptune-sized planet orbits very near to its parent star, then there will be a drop in the brightness of the star, and that drop will be periodic. Now, if there are more than one planet, then this drop will be also modulated, and there will be several sub-drop in the flux, sub-reduction in the flux. And from this reduction in the flux from this light curve, one can confirm the presence of the planet. Now, typically, this transit method is much easier to observe because here you need a telescope and an imager. However, technically, it is more difficult than the radial velocity method because here you have to remove all the noises, contamination, the telescope inherent noise, the atmospheric noise, etc. While in the radial velocity method, you need a sophisticated instrument, a high resolution spectrograph, and the instrument itself reduces the noises itself. So after you take the observation, the noise reduction is not that complicated as compared to the transit method. Now, using the Indian, so in 2000, the first transiting exoplanet HD 209458b was detected by two group of astronomers in the USA. Now, by using the Indian facilities like the Jagadish Chandra Bhattacharya telescope at Bhanubapu Observatory in Kavalur, Tamil Nadu, and also from using the Himalayan Chandra telescope and Indian Institute of Astrophysics Observatory at Hanley, our team at IIA also monitors the light curve of such type of planet, and you can see the light curve in the red, which is reduced and analyzed for the noise, and then subsequently modeled to find out all the properties of the planet. So this was done by one student, Aditya Chakraborty. We will take your the classes in the second half. Then recently we have done for multi-wavelength transit observation also. This is by another student, Suman Saha. So by using these two telescopes, we by using transit method, we found the parameters of the planet is in such a accuracy that now this is considered by NASA as the default value for the parameters or various physical parameters of these planets. Nevertheless, before 1995, we knew 9 planets only in the solar system. We didn't know anything out of it. So after 1995, the first discovery of Pegasi 1951 was so many planets. All the astronomers, almost all astronomers with whatever available telescope was there, they started hunting for new planets, and very soon, every month and every year, the number of planets outside the solar system started increase, and that gave rise to a controversy whether we could still consider Pluto as a planet, because we discovered planets which are much bigger than Jupiter. So consequently, in 2006, the International Astronomical Union decided by voting that Pluto is no more a planet, and therefore in the solar system we have only 8 planets. And before 2006 and after 1995, the search for exoplanet was confined by the ground-based telescope. So the search distance was confined within 300 light year of a radius. But after the discovery of a large number of planets outside the solar system, it prompted NASA to launch a space telescope. And we watched all
10,
those things in
9,
2009.
8, 7, 6, 5, 4, 3, 2. Engine start. 1, 0, and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Vernier engine chamber pressures are building. Groundlet solid motors are building chamber pressure.
And yeah, we got a dedicated 1-meter telescope, Kepler telescope in space for the only purpose of discovering planets. And once Kepler was functional, hundreds and thousands of planets was discovered, which has revolutionized our concept of planetary science. Now, with the launch of Kepler, the search region also extended 10 times. Now we can search around 3,000 light year from us in a narrow cone. So once the Kepler started giving us the data, we discovered a large number of planets with various property, and the diversity is so high that we could not even imagine such type of planet could exist. There are planets which are almost double than Jupiter. There are planets which are 10 times heavier than Jupiter, but they are very near to their stars, and therefore they are so hot that even iron could also melt. And there are planets which are the size of Neptune, also very hot Neptune. Now here in the solar system, we do not have any planet which are intermediate between the rocky planet and the gaseous planet, but we discovered some sort of planet which are called mini Neptune that are intermediate between the rocky planet and the gaseous planet. And then we got planet which are made of mainly carbon. We discovered planet around around binary stars, that is a circumbinary planet which has 2 parents instead of 1, and their day and night and their seasons are determined by 2 stars. So the Kepler has discovered such a diverse kind of planets that our entire concept on planetary science got revolutionized. In the meantime, some big ground-based telescope and the Hubble telescope also imaged some of the planets directly. Like the first planet that was imaged was around a failed star called brown dwarf, which is 2 mass 1207b. So the failed star, by star we means that when an object at its center, it continuously has a source of energy, and that is by nuclear energy. So that is possible only if the object is at least 80 times Jupiter mass. Now, if the object is just 13 Jupiter, more than 13 Jupiter mass heavier, then it ignites deuterium at its center, but it fails to ignite helium in its center, and therefore it fails to sustain nuclear burning inside. And that phase, that is the object which are intermediate to planets and the star, whose mass is between 13 Jupiter mass to 80 Jupiter mass, are known as brown dwarf. So this brown dwarf was also discovered in 1995. At the same year, planets was discovered. So in 2004, a object is discovered, which is a planetary mass object, That means this red object is the planetary mass object whose mass is less than 13 Jupiter mass. So even the deuterium could not burn here. But the parent star is a brown dwarf. So deuterium could burn, but helium could not burn. So it could not become a main sequence star. And this was an outstanding discovery and the image. Subsequently, there is a planetary system HR 8799 BCDE was discovered by NASA's Hubble telescope and Keck telescope in 2009. Here you can see 4 planets are orbiting, and then Beta Pictoris B, one planet, and along with is the planetary disk. The was also the when a planet is formed out of protoplanetary disks. So the remnant of this protoplanetary disk is still visible. All these planets are visible because they are quite young. They are less than 100 million years, and they are still contracting, and therefore they are extremely hot. Their temperature is very similar to a brown dwarf. By the way, brown dwarfs are visible because they emit copious amount of infrared radiation, and also in the optical they are not very. But the planets, the only problem is that they could also be visible, but they are hidden in the brightness of their star. Now these planets which are imaged, they are far away from their stars, around 30 astronomical union, or where the unit, or where the Pluto is orbiting at that distance. So astronomers block the starlight by an instrument called coronagraph, and by blocking the starlight, they take the image of the star. Then subsequently, some of the planet is discovered which doesn't have a star at all. They are rogue planets. So we do not know that how they are formed. They could be detached from a planetary system, or they could have formed like a brown dwarf. So from the collapse of the interstellar cloud, just like a star is born. And this type of free floating planet in the solar neighborhood are plenty, but they are very faint. So it is very difficult to discover them. This Pan-STARRS or many other telescope which is infrared could detect such type of planet. Now, these type of planets are special planets. They are giant, they are big, some they are within 2 stars, or they are rogue planets or lonely planets. So our ultimate aim is to find out the planet which will be habitable, where there could be life, because the ultimate aim of our search is to find out the possible answer to the eternal question, is anybody out there? So now where to find out such type of planet which could be habitable? Now, suppose there is an intelligent species, much more intelligent than us, and they are also very curious to know if there is any intelligent life in our galaxy. But out of the 200 billion stars in our galaxy, even if they have a very super million times faster computer than that we have, they could not search for all the planets. So they will take some clever way. What they will do, they will see the part where of the galaxy where the planets could be habitable, and that is called the galactic habitable zone. Now, you know, the center of our galaxy is a very hot place. At the center, there is a massive black hole, million times more heavier than our sun, and all. There must be a black hole there, and all type of X-ray, ultraviolet rays, and activities are going on. So therefore, this center region, if even they have planet, they cannot have life. And if there is a life, that life will be destroyed from that region. So beyond this center region, as you move towards the edge of the galaxy, the amount of heavier elements reduces. So at the edge of the galaxy, the amount of heavier elements like carbon, iron, etc. will be so less that even planet cannot be formed, let alone forming of life. So the intelligent life will decide that this green area, that is from the outside the center to not appropriately edge, or the in between, this green area will be the galactic habitable zone. Now, even this arm, the spiral arms are also very active. New stars are formed, and they are died through supernova. So they are also very active region. So if there are planets, there could not be life. The life cannot be survived. So the gap between this spiral arm will be the appropriate place. And in one of the gap of the spiral arm, Orion, our sun and our solar system exist. So by using their very advanced telescope, they will detect our star sun, and they will find all the 8 planets orbiting around the sun. And out of the sun, they will find out a region where life could exist. And what is that region? That region is called the circumstellar habitable zone. This term circumstellar habitable zone was coined by Su Wang in Astronomical Society of Pacific. So it means that a region around a star where the temperature because of the star is such that water can exist in liquid form. So that's called the habitable zone. Now clearly that depends on the distance of this habitable zone from the star depends on the stellar luminosity. Now if this extraterrestrial intelligence, they consider the luminosity or the brightness of the sun, and then they will find that all the three planets, that is Earth, Mars and Venus, are in the habitable zone, and therefore their temperature is such that under normal condition water can exist in liquid form. But all objects, all planets have some property that is called the reflective property, that is the albedo. So a certain amount of light that falls from the stars get reflected out to the space. For Earth, 30% of the starlight it received get reflected outside the space. And therefore, the mean temperature of Earth should have been minus 15 degrees Celsius. From Venus, a whooping 75% of sunlight get reflected. As a consequence, although Venus is very near to, much nearer to sun than the Earth, its temperature would have been minus 40 degrees Celsius. On the other hand, Mars is already far away from the sun, and so if we consider, and Mars reflects about 20% of the sunlight it received, so its temperature would have been minus 55 degrees Celsius. Therefore, if the extraterrestrial intelligence consider the reflectivity of this planet, they will find that none of the planets in the solar system is appropriate for water to exist in liquid form, and therefore life is not possible in any of the planets, because in that case the habitable zone has to be much nearer to the sun, in between Mercury and Venus. But we know that in Earth we have appropriate temperature. In fact, in Earth water exists in all the three forms: gas, liquid and solid or ice form, and life exists here. Earth, we know, we very well, we are the proof. We are talking here, we are attending the class, we are the proof that this planet is habitable. So what happened, how come Earth is not minus 15 degrees Celsius? So that happens because of an effect called greenhouse effect. When the sunlight enters to the atmosphere and hits the rock of the Earth, it then try to escape back into the space, but with a weaker energy. So it wavelengths from the visible, it changes to the infrared region, and infrared region, we know that the wavelength is longer, and the energy of this light is much weaker. So while it is trying to escape the atmosphere, it gets scattered by the different molecules in the atmosphere, namely by water molecules, by nitrogen molecules, by carbon dioxide molecules, and all these molecules. So this carbon dioxide and water molecules, it plays as a agent. It scattered this light, this reflected light in infrared so many times that finally this light cannot escape to the space. It get confined within the atmosphere, and thus increasing the ambient temperature of Earth atmosphere. This increase in the temperature is called the greenhouse effect, and carbon dioxide, water, they act as greenhouse agent. So this greenhouse effect increases the temperature of Earth by 30 degrees Celsius, making the mean temperature from minus 15 degrees Celsius to 15 degrees Celsius, so that water could exist on Earth. On the other hand, Mars has a very thin atmosphere, and therefore it doesn't have an effective greenhouse effect. Therefore, its temperature remains almost the same. It from minus 55 degrees Celsius, it becomes minus 50 degrees Celsius. Although in the summertime, temperature increases a bit because it has an elliptical orbit. At the other hand, Venus has a very thick atmosphere, And although its reflectivity is 70%, because of this thick atmosphere, it has a runaway greenhouse effect in such a way that its temperature increases by 500 degrees Celsius. So from minus 40 degrees Celsius, the temperature of Venus rises to about 450 degrees Celsius. And thus, Venus, although is not the nearest planet of the star, it is the hottest planet on of this planet of the solar system. So naturally, Kepler and other telescopes started searching for planets which are in the habitable zone of their star. But a planet is, if only it has environment appropriate for water to stay in liquid form, is not sufficient. It has to be a rocky planet also to retain the water. So in the beginning, there was many giant planet, was quite a few giant planet was discovered around the habitable zone of their star, but they cannot retain water. So Kepler and other telescopes started searching for rocky planet in the habitable zone of their stars, and very soon quite a few potentially habitable exoplanets was discovered by these various telescopes. And even you have heard in the newspaper that there is a system called TRAPPIST-1, which around which there are as many as 7 planets, and all our rocky planets are orbiting around. Out of these 7 planets, 3 are in the habitable zone. But the question is that if a planet is in the habitable, is a rocky planet is in its habitable zone, it has rocky surface for retaining water, and it has appropriate temperature for water to exist in liquid form, can it be habitating? Can it harbor life? Then we move to a more fundamental question, what is life? And we land to a newly developed subject called astrobiology. Unfortunately, we do not have a definition of life. So say 400 years ago, if somebody would have asked you what is water, in the absence of any definition, you would have described, oh, water is a liquid, colorless, odorless, and it flows from top to bottom. But at the same time, description is not at all complete, cannot give a complete idea of the object, and it could be often controversial if somebody comes with a beaker of ethyl alcohol and tells that, look, this alcohol is also colorless, odorless, and it is also liquid, it falls from top to bottom. Then how you will distinguish these two? By observing. But now if somebody asks you what is water, even a class 10 student will tell that, oh, water is a molecule made of 2 atoms of hydrogen and 1 atom of oxygen. Now from that fundamental formula H2O, one can derive all the physical and chemical properties of water. Unfortunately, such type of fundamental definition for life is not there, because life is a very complex and complicated system. It's so nevertheless, NASA has given a working definition of life, that life is a self-sustaining chemical system capable of Darwinian evolution. But that doesn't tell anything, far away from what we see on Earth. So we have only know life on Earth, and that's a vast diversity of life on the Earth, from amoeba to blue whale, from fungi to big tree. So now here in the life on the Earth also cannot be defined. So you have to resort to the description. So if you extend this NASA's working definition to Earth's life, then we can say that the Earth-based life is an ensemble of organic compounds governed by a self-sustaining synchronized system of chemical process and characterized by metabolism, replication, and evolution through natural selection. Unfortunately, most of us who opt for physics, they throw their biology books immediately after high secondary. In fact, I also did it, but now I regret for this, because now I understand how interesting is life science, how important the life on Earth, how complicated and how fascinating is the biology of the life or the living creature we observe it. So what is this these organic molecules? Now, organic molecules are the compounds made of carbon with at least 1 hydrogen atom. So the simplest organic molecules is methane, that has 1 carbon atom and 4 hydrogen atom. Now, with the carbon, many hydrogen and many other elements can be joined oxygen, nitrogen to make big chain of organic molecules. Now, so therefore, the life on Earth is carbon based. Now, for 50 years, we thought that these organic materials on Earth were synthesized on the Earth itself through an experiment called Miller experiment. So they got the Nobel Prize because of that experiment. What they showed that under certain condition, that is sparkling in the sky, organic materials can be made out of inorganic material. But now we see that from most of these asteroids and the comets, they carries the organic materials from outside. Even we know that a certain star called AGB star, asymptotic giant branch star, at the end of its life, it produces copious amount of organic molecules. Now we know that carbon is the fourth most abundant element on the on our universe, and it has valency 4, the maximum valency 4, so it can combine with several other atoms to form many kinds of elements, and these properties are not there in any other elements. So therefore it is quite natural that the nature preferred carbon to be the base of life on Earth. Now somebody may ask that life could be formed by other elements like aluminum or like even silicon or other things. But the thing is that we know that the laws of physics are same everywhere in the universe. If we throw an apple up, it will fall to you because of the Newtonian gravitation. We know Faraday's laws, and everything which is valid in Earth, they could be valid in the other corner of the universe. So basically the biology is based on the chemistry, and chemistry is based on the fundamental of physics. So there is no reason to believe that the laws of biology will be different at different places. But still, if we believe, then first we should understand what is Earth-based life, how complicated it is. So Earth-based life is carbon-based, that is an ensemble of organic molecules characterized by metabolism, and this metabolism is actually a rechargeable battery. The body acts as a self-sustaining rechargeable battery. So what is the
hydrolysis and
metabolism?
dehydration synthesis? Metabolism, or body chemistry, is often used to generally describe all of the chemical reactions that occur in body cells. The two major types of metabolic activity that occur in the body are catabolism and anabolism. Catabolism is the breaking down of complex molecules to form simpler ones, and oftentimes during the process release energy. The release of energy is related to the disruption of chemical bonds. One of the important types of catabolic reactions is called hydrolysis. Hydrolysis is a chemical breakdown of a compound due to a reaction with water. So a water molecule is added to break down a larger molecule into smaller molecules or subunits. Hydrolysis of sucrose or table sugar breaks the large molecule into the smaller molecules of glucose and fructose. Hydrolysis of protein breaks it down into smaller molecules of amino acids. And hydrolysis of a fat molecule breaks it down into its smaller subunits of glycerol and fatty acid molecules. Some of the energy released by catabolism is heat energy that keeps the body warm. And much of the energy released is transferred to a molecule called adenosine triphosphate, or ATP. Anabolism describes the many chemical reactions that take place to build larger, more complex molecules from smaller subunits. These reactions require energy, which often comes from the breakdown of ATP, which was just mentioned. One of the important types of anabolic reactions is called dehydration synthesis. In dehydration synthesis, water is removed as the larger molecules are formed. Anabolic reactions use energy to form larger carbohydrates, fats or lipids, and fuse amino acids together.
So this is one of the equation, one of the chemical reaction. Then this glucose, which was formed due to the hydrolysis by the breakdown of bigger molecules, get this oxidized by the oxygen we take by inhaling, and then it produces energy. In this way, there are several thousands of chemical reactions that is occurring, and that makes a living cell or a living body a chemical factory that generates the energy. That energy is used to warm up the body and to produce new cells and for new movement and everything. So this is metabolism is a very important characteristic of life.
Hydrolysis and dehydration synthesis. Metabolism.
Then comes the replication. So replication, but through replication, the cell divides, and there are two types of replication. One is called mitosis, where a cell makes its exact copy, and it helps in growth, in repairment, or in maintaining the body or in the body cell. So this replication has important property, the mitosis, that is through the cell division. Now there are another kind of replication or cell division that is called meiosis, and through the meiosis, the cell the information from one cell is transferred to the next generation of a living cell. Now, all this replication process, mitosis or meiosis, in fact, meiosis has two kinds of division. In first division, it is very similar to mitosis, like the cell division, and it produces two diploid cells, but then again it divides into two haploid cells, which haploid cells move from one generation to other generation. Now this exact copy or the information or the transfer of exact information from one body to one generation to other generation is carried out or controlled by the double helix or the DNA, which is a molecule called deoxyribonucleic acid. And in the deoxyribonucleic acid, the nucleic acid adenine, guanine, cyanine, and cytosine are placed in such a sequence that is called the gene. That is the gene sequence, and this sequence gives the instruction to the protein how to do it. These DNA molecules are contained in a packet called chromosome, and the number of this chromosome determines the species. So, for example, the human body has 23 pair of chromosome, that is 46 chromosomes. So when the cell divides, then this chromosome also divides, and each cell again contains 46 chromosomes. So this is the replication method, which is also a very important properties of life. And then the evolution through natural selection, which is a mistake by the gene. So while making the perfect replication, the gene sometimes makes a mistake or intentionally make a mistake to adapt from the nature, and various species are born, and only those which survive, which have the capacity for survival, exist, the other get extinct. So these three processes the characteristic. But since we cannot go to a planet and to see it from that, so how to tell that a planet has life or not? So what we will do, that we'll see the signature of life in a planet. So for example, this is called the biosignature. So for example, if we take the spectrum of the three planets, Venus, Earth, and Mars, we will see that plenty of carbon dioxide in all the three planets, but the Earth has the signature of liquid water. At the same time, the Earth has the signature of oxygen molecules and a molecule called ozone. Now, these oxygen molecules was not there when the Earth or the planet was born. About 2.9 or 3 billion years ago, a bacteria called cyanobacteria started photosynthesis, and thus it converted carbon dioxide into oxygen molecules, and suddenly the Earth atmosphere became oxygen rich. A certain amount of oxygen also came from volcanoes or plate tectonic, and suddenly the Earth become the Earth's chemistry, the atmospheric chemistry got completely changed, and the life which were formed before that, which was anaoxygenic, which was surviving without oxygen, they for them oxygen molecule become poisonous and they could not survive. And the life which survived through the oxygen, they evolved and they existed. Now this oxygen molecule, when it goes to the upper atmosphere, it gets dissociated with the ultraviolet rays of the sun into oxygen atom. Now this one oxygen atom is combined with the oxygen molecule to form a molecule called ozone. So in thus, a ozone layer is formed above the earth, which is protecting us from the energetic ultraviolet rays of the sun. So this ozone layer is a product of biological activities. And moreover, in an oxygen rich atmosphere, methane cannot survive. The chemically naturally made chemically produced methane cannot survive. So in the earth atmosphere, we still get the signature of methane, and because of the living activity, because of the living cell, when it died and then it disintegrate into methane, and there is a continuous pump of methane, and methane is in equilibrium in earth atmosphere. So we will search for oxygen molecule, for methane molecule, for ozone molecule in all this habitable planet. But the current technology prohibits us to take such type of high resolution spectrograph, which can show us the signature of this biosignature. But in the same process, we model and we determine how to do it, we know it. So this is called transit spectra. So how we will take such type of spectra of the planet to determine the biosignature? Now, when a planet transits its stars, it blocks the starlight, but certain amount of starlight passes through the atmosphere of the planet if there is a atmosphere in this planet. So now, when the sunlight or the starlight passes through this atmosphere, it carries the signature of the atmosphere, or it get absorbed by the atmosphere of the planet, and then it carries the signature of those molecules. This is defined by some quantity called transmission depth. I think in your tutorial class, Arithro will teach you how to calculate this transmission depth and how to make the transmission spectra. So basically, it is the difference of in the spectra when there is a transit and when there is a no transit. So when there is a transit, there will be a molecular feature in the spectrum which is not there in the star, but when there is no transit, so there will be no molecule in the star. So by subtracting the spectrum during the transit and from not the transit, we can find out the spectra of the planetary atmosphere. And now with high resolution spectroscopy, we look for the presence of molecule, the various kind of molecules in the planetary atmosphere. And the day when we'll get a very good telescope and a very sophisticated instrument, who knows that we can find out the biosignature in some of the habitable planet. Nevertheless, we need also new method. So we propose another method through which biosignature can be determined, and that is known as so these are the model we have made. I think Arithro will tell more about it in the tutorial class. We have already predicted that what will be the signature and how it will make. So in the case, we'll go that for the new mechanism that we have proposed, and this is called the polarization. Now, what is polarization?
What is polarization? Technically speaking, polarization is the measure of the anisotropy of a radiation field. Light is a wave of electric and magnetic fields. These waves can be oriented in any direction. The direction of each wave's oscillation is called its polarization. Most light sources, including natural light, produce randomly oriented waves. We call that light unpolarized. However, if the light waves are in the same direction, we say they are polarized. A device called a polarizer lets us measure light polarization. A polarizer allows light of the matching orientation to pass. It blocks light of the opposite orientation. Unpolarized light will pass through the polarizer at any orientation. Now, how does light become polarized? Light becomes polarized either by the presence of a magnetic field or when light scatters off of a surface. A properly oriented polarizer can block this reflected light. Light can also become polarized from scattering off of gas and dust particles in an atmosphere. You can see this effect in the sky by rotating your head while wearing polarized sunglasses. The amount of light that gets polarized tells us about the gas and particle properties in the atmosphere. Polarization studies have helped us understand the atmosphere of the other planets in the solar system. The unpolarized star light becomes polarized when it scatters off high altitude haze or cloud in the atmosphere. However, if the atmosphere is uniform, the cloud is distributed homogeneously, or if the object is perfectly spherical, then the net polarization becomes zero, as the polarization in all directions cancel out. But if the cloud is distributed inhomogeneously in band-like structure, or if the object is oblate because of its rotation on its own axis, like our Jupiter, Saturn, or Earth, then the net polarization becomes non-zero. On the other hand, if a planet transits across a star, or a satellite or exomoon transits a planet, then also the net polarization can be non-zero.
So in this way, we have also predicted how to detect exomoon or moon around extrasolar planet, which is yet to be discovered. No exomoon has been discovered yet. But unfortunately, our technology still lags behind, and within another decade, we are going to get some more sophisticated instrument to play with. So all these four, Hubble, Spitzer, Kepler, and TESS, are functional, and they have already given the result. Now by next year, hopefully the James Webb Space Telescope will go, then WFAST, and then the USO will also send Ariel, with whom we are also collaborating. This will be a dedicated telescope in the space by the European Space Agency to take the transmission spectra of planet. Now in the ground also we have Keck telescope and large binocular telescope, but within a decade we are going to get three giant telescope, next generation telescope. One is European extra large telescope, one is 30-meter telescope, of which we are with India are partner, and then giant Magellanic Cloud. So we know that the diameter of the largest telescope, that is Keck telescope, is 10 meter. Now this European extra large telescope will have a diameter called 42 meter, and the 30 meter will have a 30-meter telescope. So it is that big. On the other hand, the JWST will have a mirror much larger, so its capacity will be at least 3 times more than the Hubble Space Telescope. So we hope that with this next generation space and the ground-based telescope, we'll be able to take the spectrum from the exoplanet, especially from the habitable planets, and hopefully out of some of the planets we can detect biosignature, and then possibly answer the eternal question if we are alone or not. But before we discover the planets outside the solar system, let us come back home and see how rare, how is our own planet, which is the only known habitating planet right now.
That's Earth, that's home, the third planet of an ordinary star called the Sun. An extremely rare combination of astronomical and geological coincidences enabled life to origin, survive, and evolve on it. From a distance of about 10 million kilometers, the Earth looks like a blue marble. As we move further and further, the planet appears as a pale blue dot floating in the vast emptiness of space. So special,
yet so vulnerable, so crowded, yet so lonely, so common, yet so unique, so insignificant, yet so great, a mote of dust suspended in a beam of sunlight. So we do not know how life originated on Earth, whether life was formed on Earth itself or it was brought back by asteroid or by comet from outer space. But what we know that is the survival or the existence of life is so critical, so complicated that there could be very few planets where even if life originated, it has survived, because space is a dangerous place. So a collision by a comet or a giant asteroid can finish us within a moment. And we suspect that around 60 million years ago, during the Jurassic era, such type of a collision by such type of comet has extinct most of the evolved life on Earth, including the dinosaurs. Now, if there is a supernova explosion by a nearby star within 10 light years, then the intense supernova explosion, I think you know that when the massive star dies, it explodes and it emits copious amount of energy. And if a supernova explosion by a nearby star happens within 10 light years or 30 light years, then the amount of ultraviolet ray that will completely destroy the chemistry of the Earth atmosphere, and life will be completely extinct. Gamma ray bursts in our galaxy, gamma ray bursts are the most powerful energy source in our universe. So when two black holes or in two neutron star or a neutron star or black hole collides, that gives a gamma ray burst. So if one gamma ray burst occurs in our galaxy itself, then the amount of energy that will produce, that will be enough to destroy life instantly. Now, in general, the sun is a gentleman. It is a middle-aged dwarf planet, and it is not that active. But if some problem happens to the sun, if it becomes very much active and a giant flare could come penetrate the Earth, it can destroy the magnetic field of the Earth, and it could also change the chemistry of the atmosphere. It can make the Earth atmosphere completely poisonous. But these astronomical possibility, this hazard, the probability of this hazard are very less. We now do not know that if there is a comet, the possibility of this comet and giant asteroid has been reduced because of the presence of the giant planet like Jupiter and Saturn. So the birthplace of these comets are the Kuiper belt, and when this Kuiper belt object or even far away from the from where the long born comets are born, they come towards the sun. They are attracted by the giant planet like Jupiter, Saturn, and Uranus, and most of these comets falls over them, and so the probability of a collision with comet is reduced because of the presence of the giant planets in the outer region of the solar system. Now, we don't know any star nearby which has completely finished its nuclear capacity or which is going to explode. So similarly, we have no information that if there is suddenly a black hole or neutron star will collide and how the sun. But then even if the astronomical hazard, the possibility is less, it remains. At the same time, there are terrestrial calamity or hazard is possible, like super earthquake, super tsunami, or volcanoes might destroy the evolved life on the Earth. But these are, although these are very small possibility, the imminent disaster is man-made disaster. So a nuclear or chemical or a biological wear can destroy the atmosphere irreversibly, so that the atmosphere will become radioactive and poisonous, and all life could extinct in a certain duration. At the same time, the global warming, the civilization needs energy for that, factories and other things are coming, and the Earth is getting warm, and very soon it may happen that the carbon and silicon cycle that maintain the temperature of the Earth can be broken and the earth becomes so warm that even the ozone layer can become destroyed, and the ultraviolet rays can enter from the sun, and it will destroy the living cell, and it will extinct the life. So therefore, it is our duty before, while we search for new planet, where we search for a possible answer, whether we are alone or not. Believe it or not, Earth is right now the only planet where we exist, we survive, and there is no place nearby where we can migrate in near future. We have not yet got any planet which is very similar to the Earth, even within 3000 light years around the sun. So therefore, it is our duty, it is our responsibility to protect this planet Earth, which is blessed by Earth, so that generations of children can keep smiling in this planet. Thank you.
Thank you, Susan, for a wonderful walk through the history and bringing us up to the current time. So there are many questions. So it's going to be a long discussion.
Before I answer it, I will suggest people that you can tell your college library, or you can buy a copy of my book, Worlds Beyond Our Own, which has much more in details whatever I have talked. So in IIA library also one copy is there, and I think you should recommend to your college or your university to get this book. This is written for non-expert, published by Springer. It is available in Amazon and Flipkart or from Springer. Okay, so now I am ready for your question. Let me first stop sharing the thing. And
okay, yes. So there are I'm going to first take questions from YouTube. Okay, so I'll read them out. So the first question is from Awasti, and I don't know, it's he or she is asking, is transit method used when the star itself does not revolve?
The star is revolving means you mean the spinning of the star. Yes, the star is also spinning, but the spinning is very slow. For the sun, it takes almost a month or more than a month before it makes one revolution. But the planets, they take sometime 2 days, sometime 4 days, sometime 10 days. But if the planets are far away, then they will orbit like Earth type of thing. It takes 1 year. So the revolution of the stars, it can be calculated from the spectrum of the star, and then we can find out that if this transit is because of any star spot or anything like that. So the star spots also are not permanent, so they can go, but the planet will remain for a long time. So I understand your the question you are asking, that whether because of the revolution a star spot can give a false positive signal, but it is not, because we make complicated analysis and we see the size of the star spots, and we see the distance and all those things, and we remove all type of noises, including the star spots, before we confirm that it's a planet.
Okay, so next question is from Priyash Mistry, and the question is, why they use iodine cell as a reference in radial velocity method, not any other material?
Yeah, that was an old thing. That is in 1995, and around that time the iodine cell was used. Nowadays they use the argon cell, because these are very deep in the thing. You have to know that you have to identify those lines. So it is because of the convenience. And what happened, that in the instrument they put iodine gas or argon gas, so that there will be a reference system. Now in the laboratory, this whatever line will be formed, that will be fixed. So from the fixed laboratory iodine line, that is the starlight, will also be absorbed by this laboratory line, but then the iodine line in the star, that is moving. So this iodine or argon is picked, and in the instrument they are calibrated by putting iodine and argon. So there is nothing but iodine line is very distinguished line. It is very strong line, and that's why it was picked. But nowadays, usually the argon is used.
Okay. Okay. So now we will take questions from the Zoom session. So we will allow them to unmute and ask. So the first question is from Satya. Can you unmute and ask?
Yes, ma'am. Ma'am, what if the planet were in a face-on orientation with the Earth? How could we detect with these methods, transit and RV method?
No.
Will that be possible?
No, we cannot detect if an exoplanet is in face-on. In fact, if the inclination angle of a planet is less than 70 degree or 75 degree, then the transit method or even radial velocity method cannot discover it. But there are other method that I have not mentioned is the Isometry method in a binary star. If there is a planet, so from the movement of the star, or there is a gravitational microlensing effect, from that we can detect such type of star whose inclination angle is very high. But gravitational microlensing, once upon it was a popular method through which quite a few planets was discovered, but it is a chance effect and it cannot tell the size or the mass of the planet, neither it can tell the inclination angle of the planet. So you are right that face-on planet, or even those planets which are orbiting inclination angle less than 75 degree, cannot be discovered by the existing method, and they can be imaged. However, if they are quite young or they are very hot, like this HR8799b, but these two methods cannot detect planets which are not ozone.
Okay. So next question is Shiva. Shiva, can you ask? Okay, he doesn't.
Excuse me, sir.
Yeah.
Come on.
Am I audible?
Yes.
So, are these methods like the transmit method and all are applicable to rogue planets for finding?
No. Rogue planets are directly imaged because they are not around a star. What is rogue planet? Which doesn't have a star, which doesn't have a parents. So rogue planets are freely floating planets. So they don't have a star. So if you remember my talk, this transit method or radial velocity method is the effect on the star by the planet. So for the rogue planet, there is no star. So there is no question of radial velocity of transit. So these rogue planets are discovered only by the direct infrared emission from them. So they are very near and they are very hot. So they are bright in the infrared. So the infrared telescope like PAN or the WISE, that is wide infrared telescope, they can detect such type of planet. But it is believed that there are thousands and millions of such type of rogue planet, but there is no way to find out such type of faint planetary object which are orbiting freely.
Thank you, sir.
Okay. So I think Shubhakanta's question is already answered by Satya. So I'm going to move on to the next. Next question is by Omkar Gupta. Gupte, sorry.
Hello, sir. Hello, sir. Am I audible?
Yes. Please go on.
Sir, I want to ask that is there any possibility of misunderstanding a big asteroid or a dwarf planet as a planet in transit method, sir?
So comet, how many times have you seen a comet and how many times have you seen a planet in the solar system? So the comets orbit in a very long period. But here in the planet, you see, when we discover or when we find it out, we have to repeat the thing. We have to repeat the whole thing there, and then several type of, sometimes 20 times even we repeat this transit epoch. But whereas the planet, what happened after 1 year, the comet, or after few months, the comet will vanish from there. There will be nothing was there. So such type of comet is also discovered, and there is one star called Becky star that is supposed to be. Initially, they thought that it has a extraterrestrial intelligence playing with its stars, but it happened that most probably a comet has broken up and those debris are blocking the star sometime. So one comet is all discovered, but we can very well distinguish between a comet and a planet from its period. For the comet has a highly elliptical orbit with a very long period, whereas the planets are mostly circular orbit and they have short period.
Okay, so the next question is by Sri Bala, which is probably already answered, but I will let her speak. Sri Bala, please unmute.
Thank you, ma'am. I too was having the same doubt that Omar Gupta had asked. So thank you, sir, for the answer.
Okay.
Okay, welcome.
Okay, next question is by. Okay, I will let Shubhakanta speak now. So Shubhakanta, can you ask your question?
Hello.
Yes.
Sir,
Yes, you are audible.
how detect the planet which are small, there less impact on radial velocity?
No, I could not get your voice is breaking.
Okay, maybe I'll read it out. Okay.
Yeah.
He says how to detect small planet which has small impact in radial velocity.
If the small planet is very near to their star, then their impact will be sufficient. But the existing telescope can measure the radial velocity as low as 10 meter per second. That is the Earth type of planet. So this radial velocity on the star imparted by the planet on the star depends not only on the mass. It doesn't depend on the size. It depends on the mass of the planet and its distance. So if a small planet is very nearer to the star, it will impart a good amount of radial velocity, and from that one can detect it. But to find out the size, one needs to go with the transit method. So even the radial velocity gives only the projected mass of the planet. So once a planet is discovered through the radial velocity, one has to go with the transit method and then find out the inclination angle that will give the exact mass of the planet and the size of the planet. And from that, we can make the mean density of the planet and all the other properties. So it is a combination of radial velocity method and the transit method that gives us the full picture of a planet. So the answer to your question is that if a small planet, even if it is smaller than the Earth, is nearer to the star, much nearer to where the Earth is there, then the radial velocity will be more than 10 centimeter per second, and within the range of the current instrument. Now, with the development of the technology, we'll improve this our instruments, and then very soon we can discover even radial velocity 1 centimeter per second. As I have told in my talk, the Earth imparts a radial velocity 10 centimeter per second to the Sun, whereas Jupiter imparts a radial velocity 12.4 meter per second. The first discovered exoplanet 51 Pegasi B imparted as much as 50 meter per second radial velocity to its star, and Michel and Didier was completely surprised to see such type of huge radial velocity, because so far we didn't know that a planet could be so near to their star. But now we know that so many giant planets are near to their star. Even our solar system is an exception where the giant planets are outside in the outer region. But what we have discovered, it may be the bias in our observation, that we can detect only the large planets which are very near to their star.
Okay, so next question is Arya Dattamunshi. You can.
Hello.
Yeah.
Yeah.
Yes, sir. So you said that rogue planets are free floating, but isn't there a possibility that rogue planets will face gravitational attraction from surrounding bodies?
Yes, so that is possible, and that's a very interesting thing. So that tells that how nature plays with us. Suppose there is a planet which was in a star that was carbon rich, and then it got detached from that planetary system because of some perturbation, or because it was completely outside like that and it was floating. Then suddenly it came to the nearby another solar system which is oxygen rich like our sun, and then it get attached with it, then we, the astronomer or other astronomer, will get surprised that how come a carbon rich planet is in a oxygen rich star. So that will make mysterious thing for us, but that is possible, of course. But so far we could not have discovered. You know, there is a prediction that there exists a 9th planet in our solar system, and there is an intense search is going on there. But we do not know so far. WISE has told us a limit that it cannot be heavier than Saturn. So it could be like a Neptune or a super Earth. But if such type of planet exists far, far away from even beyond the Kuiper belt, there is a possibility that in future, because of the gravitational attraction of a passing star, it may be detached, and then it will freely float in the interstellar medium. Then it may come very near to the Alpha Centauri and may combine with the Alpha Centauri, and then that will be very curious thing and very surprising thing, and it will be a puzzle for the human civilization to resolve it. But these are all speculative things. We have not yet discovered any carbon planet in a oxygen-rich solar system. So getting detached and getting captured, the possibilities are the extreme end. So getting detached, the possibility is quite high, but getting captured is very less, because the interstellar between interplanetary medium or the interstellar medium is so vast. You know, our nearest star Alpha Centauri takes 4 years for light to reach us, whereas we get sunlight within 8 minutes. So imagine the distance between these two. So getting attached is extremely difficult, but getting detached, it depends on the planetary system itself.
Okay, next question from Akash Kumar.
Yes, my question is that the picture you saw of galaxy, how we design the picture, because no direct images are taken from any satellite or any.
The galaxy picture, that we take the stars pictures and then we make it there. You can get a, you Google image and our galaxy, you will get it. I downloaded that our galactic picture. So we have we cannot see the galaxy here. We have an idea that our galaxy is very similar to the spiral galaxy like Andromeda and other thing. But from the star formation, from the star position of the star, from the observation, we find out that what could be the nature of our galaxy. And we also know from the activities of the center that there is a massive black hole, so how it will become there. We are not outside the galaxy, so we cannot take the image of our galaxy, but by combining all the starlight in our telescope, we can construct the image of our galaxy.
Okay, so there are other questions which are very similar, so I'm going to skip them. Next question by Channa Basawa Kalure.
Yeah, thank you, ma'am, for giving an opportunity to speak. And thank you, sir. It was a wonderful section. So my question is about greenhouse effect. Can greenhouse effect occur in any other exoplanet, or is it only limited to Earth? If it's possible, then how can we know that that planet is under greenhouse effect?
Yes, so greenhouse effect should occur wherever there is an atmosphere. Now, as I told in my talk, that we know in the solar system, because they can be resolved, that Earth has a greenhouse effect, we know very well, and we know there is a runaway greenhouse effect on Venus, because Venus's Earth is very thick. And in Mars, we know that there is not much greenhouse effect because the Mars atmosphere is very thin. So similarly, in other exoplanets, if there is an atmosphere, there could be greenhouse effect, but we may not know if there's a greenhouse effect. So we have to know, if we know the atmospheric composition, if we know that the thickness of the atmosphere through the transmission spectra, then we can calculate that what will be the possible greenhouse effect on the star. In fact, we can calculate a range of the temperature due to greenhouse effect, and thus we can measure the ambient temperature because of greenhouse effect. Now, the thing is that for right now, we measure the temperature of the habitable zone, that is just by the distance of the star to the planet, and by the reflectivity. If it has the atmosphere, then we can find out the reflectivity. but we cannot determine the actual temperature in the planet. So from, if it is in the habitable zone, we can tell that this should have appropriate temperature for water to exist in liquid form. But this will be just a target for us. Finally, what will be happened, we will find out the spectra of the planet, and from that spectra we'll find out the signature of water, oxygen, carbon dioxide, and all those things. That will tell us the real picture of the ambient environment. And if there is a biosignature, we can tell that definitely it has a appropriate temperature for water to exist if there is a Earth-like planet. For the thing is that it's good that nobody has speculated that how do you know that life could exist beyond 100 degree without water, all those things. So what I have told is how to search for Earth-based life, and that's why I told about the astrobiology. So we may not know many things about this planet unless and until our technology get updated and we get high resolution spectra from the planets and from the stars. And once we get the spectrum, from the spectrum we can determine all these properties, the greenhouse effect properties, from the environment temperature, whether water exists in ocean form or any other form, etc.
Okay, so Sujan, the official time is over and we are going, it is tea break now, but there are a few more questions. So if you are okay with it,
I'm
we
okay,
can go through.
yeah, I'm okay. I'm thankful to.
Okay, yeah, we can carry on for another 6 minutes maybe.
Yeah.
Okay, next question, Gautam Sankar can ask.
Yes, ma'am.
Yes.
No, Gautam, be louder.
Okay, sir. So the doubt I had was basically for detecting habitat. We basically use the presence or absence of water as an indicator for detecting a habitable region in the solar system. So I'm just having a doubt why we are using water, because other metabolic processes could be independent of water for their systems.
Actually, you asked on the astrobiology, but your voice has broken, so I could not understand you properly. You are asking on metabolism, that only I could ask it, I could get it there. And see, the thing is that why I told this biology, that how to distinguish on that. So metabolism, that distinguishes us from a machine. Okay, so if there is a movement of that, but it is not the only method that can define the life. Replication is also another thing, and evolution is also important. For example, if in Mars you see one cat and dog, so there are two possibilities, that either if you believe in Darwinism, that either there are many more cat and dogs and many other 1 cell, 2 cell, 3 cell, even multi-cells and plants are there, or those cat and dogs are imported from Earth or from other habitable planets. So if we believe in Darwinism, but if we do not believe in Darwinism, then just one human being can stand there and tell that, look, I am life in other planets. So, but that possibility is not there. That is, so fortunately, that is not there. So similarly, the replication is there, from where replication, this evolution is a part of the replication. So everything is dependent deeply on everything, all the mechanism. So if there is no replication, there will be no growth. So one cell creature will remain in one cell. We know that for the first 2 billion years, the life was in one cell. And then the cells started dividing, and we get multi-cell and developed species, and that appeared to human being finally. So this replication is also very important, and that transferred the information from one generation to another generation. So similar way, for the survival of life, for defining the death and the living, the metabolism is quite important. Now the metabolism, whatever we are seeing, there are some extremophile which can survive by sulfide or by some other nutrients that can continue giving the energy. But all this energy basically comes from the solar energy. So we, the human being, we do not directly take the solar energy. We eat the plants. The plants actually take the solar energy and photosynthesize and then make it as a food. And we, the animals, we take this plants and we get this energy in our body in the form of carbohydrate, glucose, and sucrose, etc., etc. But now if there is a extremophiles which could survive by different chemical constituent nutrients or different without oxygen. They could survive in extreme situation. They are called extremophiles, but they cannot evolve. They cannot evolve into developed bodies or into a intelligent bodies or into a dinosaur or anything else. They will survive under extreme condition, but for a shorter period or for a shorter time, and there is no way for them to evolve into a complex multiple organ life.
Okay, so next question is from Bharat Kumar Kannan.
Good morning, sir. My question is that you were mentioning about albedo, greenhouse effect, and all while talking about the habitable zone, right? So, if on these basis we can rule Mars is outside of the habitable zone, means then on what basis do the scientists are looking for life on Mars? And I have one more question. That is, as of now, we know that life is based on carbon, right? So is there any possibility that in some exoplanet there may be some other form of life, like made up of non-carbon based?
Your second question I have answered in my talk itself, that the nature preferred why there should be different elements, why there will be a different basis of life elsewhere, when laws of physics are same everywhere in the universe. Why there should be different biology, laws of biology in different places? After all, the nature has taken the optimized path. That is, carbon is the fourth most abundant elements in the universe, and it can combine. It has the valency force, so it can combine and to form maximum number of compounds. It is soluble to water, etc., etc. So why the nature could take a difficult method? But even if I believe in your speculation that life could exist in other form, it is entirely different than what we see the art. We cannot distinguish them that they are art. So we will search only those things which we can distinguish as life, and that is the art-based life. But personally, I don't think life could exist in other form which is not based on carbon, because then the possibility of it to survive will be much more difficult for that. Now, for your first question, why scientists are searching for life on Mars, you should ask those scientists. I'm not searching life on Mars, but the thing is that Mars has a very elliptical orbit. Mars is in a habitable zone if viewed only from the sunlight. So it elliptical orbit means in the summer time in its equator becomes warmer, so that the ice, the snow, it melts and it gives to water. But that doesn't mean that Mars has a developed body like you and I, or a cat and dog. So what the scientists are looking, if on the subsurface of Mars there is a possibility that it is protected under this cold environment, some sort of one cell object or multiple object like bacteria or bacterium type of thing survive. And the science, for your information also, that scientists are searching that if once upon a time when Mars was habitable, the first few billion years, if there was life on it, if there was a life, then it disintegrated into methane. So the scientists, the probes, in even with our ISRO's probe, we are looking for the signature of methane to see that if there is any sort of micro life exist or extremophile exist in the subsurface of Mars. So there is a possibility not for evolved planet like cat, dog, dolphin, or you and me, but the scientists are searching for microbiological, micro life on the subsurface, that is under the surface of planet Mars.
Okay, so there seems to be a lot of excitement about definition of life. So people, please continue your discussion. So next, there is a question from YouTube, Chandan Shri S. And the question is, can microorganisms migrate from planet to space or other planets?
That's a very interesting question. Actually, that postulate has been given long ago, some more than 100 years ago, called Panspermia thing there. So that's still that the seed of life might have been formed somewhere in the universe interstellar medium, and it is traveling, and then while Earth travels through the interstellar medium, these seeds falls over the Earth, and then it gets a very appropriate environment to evolve and to become evolved life. So we do not know. See, the thing is that we have not yet received any signature from any comet or any asteroid that it is bringing a seed of life or life. What we know that this comet and asteroids are bringing organic material. So now the question is like Urey and Miller experiment, when we in the laboratory we made organic material out of inorganic material, then it was extrapolated that if organic material can be synthesized artificially or in the Earth atmosphere from inorganic material, then life could be also originated on the Earth itself. But now when we see that the organic material is being transported to Earth by the asteroid and the comets, we have the question that if that is the case, if we extrapolate, then is there a possibility that life is transported, at least the seed of life is transported from outer space to the Earth? But we don't have any answer to this question. So the origin of life is still under question. We do not know whether life formed on Earth itself or it has been transported from outer space. There is no answer, no specific answer to that. What if somebody tells? These are all speculations only. So unless and until we discover life elsewhere, or in the laboratory we can synthesize life artificially, we cannot answer this question.
Okay, so I think it is time to stop. Thank you, Sujan. It was wonderful.
Thank you, all the participants.
And all the participants. Yeah, great discussions.
Thanks for asking nice questions. Whoever has missed it may communicate with us through email and through Facebook, through social media. And thank you for your patience.
Okay.
So shall I leave the meeting now?
Yes, you can.
So all the participants would attend the classes taken by Auditro, which will be more technical. In fact, you can ask, whoever could not ask question can ask also question on Exoplanet to Auditro. Auditro has completed his PhD thesis, so he will be able to answer all the question. And I will also try to appear into that class, that technical class or the practical class. Okay, so don't miss that practical class by Aditya Chakraborty. Thank you.
Okay, thank you, Susan.
Thanks.
So somebody is asking for the email of the speaker. So if you go to the IIA website, you will find all the emails of all the professors, all faculty members of IIA. Please go to the IIA website. Okay, so Jyoti is around. Jyoti, are you around?
Hello?
Jyoti.
Yeah.
Okay, so you are in charge now.
Okay.
Yeah, please announce again that they should look at the IIA summer school page for the tutorial material for the afternoon session before the start of the next lecture. You can do that.
Okay.
I will log out now.
Is Sridharan around? Has he joined the meeting? Crispin? Hello?
Hello? No, he hasn't joined.
Okay.
This Sridharan.
Can anyone contact him if he has not joined yet? I can't see his name. Is he here? Hello, sir. Can you
Yeah.
try sharing your screen?
Yeah.
Yes, yes.
Let me close. Let me make him co-host first.
I get a pop-up host disabled sharing screen.
Wait.
Host disabled participants.
Just now, no, just now I assigned you. Now you can.
Okay, so in the meanwhile, please try to find the today's tutorial session on the web page, as mentioned by Prava ma'am.
And also one more announcement. Sometime there may be a
Can you see my
photo
screen?
session by tomorrow.
Yes, we can see it, but it is not on the first line. Yeah, perfect. Okay.
Is it okay now?
Yes.
Am I audible?
Yes. We'll start in after 1 or 2 minutes, maybe.
Okay. I just want to see my screen is moving. Can you see the screen changing?
Yes, it's moving.
Yes. Okay. Thank you.
Okay, so there is one announcement. The attendance for today's session will be kept open for 30 minutes and we will announce it randomly today.
And Jyoti, one more thing. By
Yes.
tomorrow, afternoon session, the first session after first talk after there may be in the during tea break there may be a screenshot with everybody's video on, like a
Okay.
photo session.
So that will be tomorrow, right?
Yeah, tomorrow.
Okay.
Right now, students are less. Let's see if the number increased. You can say it again.
How many participants do we have at this time?
Currently 156, but 208 in the morning.
208. Okay.
People are still joining, so let's wait for another.
What is the typical number?
It's around 200.
Okay.
Okay.
Yesterday final was 230. Today it is 200. 208.
All right, we can start our session now. So this session will be, so the speaker of this session is Professor R. Sridharan from Indian Institute of Astrophysics, and he will discuss about the astronomical instrumentation. So I'll give you a warning after 1 hour, sir. Okay?
Okay, the whole talk is 1 hour 20 minutes, right?
Yeah.
Okay.
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 But there is some time for questions also. So
yeah.
Okay.
Okay. Good morning, everybody. Can you all hear me? Okay, I assume you can.
Okay, sorry for disturbing. I would like to know whether you prefer the questions in between the talk or at the end of the talk.
I prefer, I think this is more at the end of the talk. I don't want to interrupt in between. They can list it down and at the end I can answer the questions.
Okay.
Okay.
Yes, please go ahead.
Okay. Let me just open my video. Good morning, everybody. I'm R. Sridharan. I work on high resolution imaging techniques, which involves adaptive optics, long baseline interferometry, spectral imaging, etc. Today, I'm going to give you a small bird's eye view of the astronomical instrumentation. It's a very vast subject, and I myself don't work in all the fields of astronomy environment. It's only a specific particular subfield, but nevertheless, I'm just trying to give the overview. So let us get started. So the what is astronomical instrumentation? It's as per this prestigious science journal Nature. It's defined as astronomical instrumentation are the tools used to observe the objects and phenomena that occur in space. These can include both terrestrial and satellite-borne telescopes. High precision optical components such as mirrors and lenses at all wavelengths in the electromagnetic spectrum are crucial to the development of these devices. So basically, in this talk, I will be covering the astronomical telescopes and the back-end instrumentation, and that too not on a wide range of electromagnetic spectrum. I will be covering only optics and infrared wavelength, at optical and infrared wavelengths, because it's not possible to cover the entire thing in one lecture. So basically, the telescope and instrumentation, the telescope could be ground-based telescope as well as space-based telescopes. And as far as as I said, is telescopes in the back instrument, the instrument types, there are different kinds of astronomical instruments. They depend on the scientific interest. There could be I've just given some 6 different kinds of astronomical instruments. Basically, astrometry, which is measuring the position of the stars in the sky, imaging, spectrometer and spectrograph, and polarimeter, coronagraph, interferometer, and the combination of all these. Sometimes we may have the interferometer, a coronagraph on top of the interferometer sitting, a imaging instrument. So a combination can also be used. So developing such back-end instrument is basically a part of astronomical instrumentation. So the technology involved here is huge. Some of you may be coming from physics background, some of you coming from the engineering background. So this is an instrumentation is an engineering subject. It also needs want to understand the basic physical principles. So anybody working in a different kind of engineering field can contribute to the astronomical instrumentation. As you go along, there are different subfields, which everything is we require multi inputs from several disciplines. Basically, we need to know what is optical and mechanical design. So this is basically optics and mechanics. And then in modern astronomical instrumentation, also demand vacuum and cryogenics technology. Vacuum is low pressure and cryogen is very low temperatures. And then we also need a software, which is essential part of any astronomical system nowadays, and the electronics, and the system engineering, which takes the overall maintenance of the system right from the beginning conceptual design and actual design, integration, manufacturing, assembly, testing, and regular operation, performance characterization, and the maintenance. Everything is included. So all these things are part of astronomical instrumentation. These are the things we will do. So the aim of this particular talk is to provide a feeling of understanding of what astronomical instrumentation is. In no way it is a complete, and also you may not really grasp everything, because I'm going to cover a wide range of topics. It may be very exhaustive, but the idea is not to give you the full, just to give you an idea of what are all things available there. Then depending upon your interest, later we can go. Basically, I will be recalling some basics of optics, because in astronomical instrumentation, we need optical design is a major part, where we manipulate the light coming from the stars and bring it to some focus and study. All we get from the star is the light. So how we manipulate the light is very important, and for that we need to understand what is the optics, basics of optics, and then optical components, infrared and optical detectors, and also I deal with the optical and IR telescope. As I said, astronomy is a very vast subject, starting from gamma rays, X-rays, visible, ultraviolet, infrared, microwave, radio, so all the full spectrum. I'm not an expert in all the electromagnetic spectrum, instrument in all the wave bands. So I'll be covering mostly optical and infrared regions. So for those who are interested in pursuing or just reading more, it's not really a textbook. It's a kind of reference guide for astronomical instrumentation by this Christoph Keller, Rama Navarro, and Brandit. These authors have written this book. It's basically a kind of handbook where you can refer to, if you want to, for details you have to go to specific textbooks, but if you want a handbook just to have a what are the concepts and formulas, we can go. This book is probably available for downloading. I'm not very sure. You can go to this website and try if you are able to download, because I am able to download because I am a member of the SPIE. I'm not sure non-members will be able to download it. So let us get started. To start with, I'm going to talk about this, refraction, reflection, and transmission, because these are the things, something which you have already studied in your high schools. Basically, the law of reflection says that the incident angle, incident ray, and the reflected ray, and the normal surface normal, they all lie in the same plane, and the angle of incidence is equal to the angle of reflection. And this is the law of reflection. And the law of refraction says if there are two media, from the light goes from one medium to other medium, where the medium have refractive indices of n1 and n2, this formula applies. N1 sin theta I, incident medium, and TT is a transmitted medium where the light goes off. N2 is the medium number 2 where light is getting transmitted. So this Snell's law applies. Now, in some most of these cases, we need to know, apply this basic formula in our optical design of the instruments. Basically, that's what. And nowadays we do have some software which can help us with these basic principles, but we can also do it ourselves. And in some cases, we'd be required to know what is the amount of light. I mean, if a light ray enters a surface and goes through, reflects, what will the amount of light we will get back, and what is the amount of light will get transmitted into it. So we need to know the total power calculation. So for that, we use normally the Fresnel equation, which is define the complex transmission reflection of S polarized and P polarized light. So this is if alpha is the angle between the electric vector of the plane of incident and arbitrary polarized light. These are the transmission coefficients, and S polarized and P polarized, and total reflection is sum of these, and transmission is given with this. I say these formulas are already there. I mean, I don't want to go into the details, but there are standard models using which we can estimate what is the amount of light transmitted, reflected. And in general, the principle, when you apply this, we should consider that whatever reflected, transmitted, and absorbed total is 1. If the indices of both materials are real, and there are no absorption in the interface. The internal transmission of homogeneous material with absorption coefficient alpha and thickness T is described by this Beer-Lambert's law. But I think all of you or most of you must have read all this in your high school or college education. So on coming back to this, another concept in polarization is basically any electromagnetic wave can have two components. In the electric field can be expressed with the two components, Ex and Ey. Any orbital direction, the electromagnetic wave propagates in Z direction, where the electric field vector is in XY plane. It can have either in X direction as well as Y direction, or it can have any arbitrary direction. And if there is any arbitrary direction, we decompose into both an X and Y components to study. So the linear polarization would mean that the components of the electric field differ in phase by either 0 or 180 degree. Circular polarization, they differ by plus or minus 90 degree. In general, the polarization, any fully polarized light can be described by a Jones vector, basically, which is basically representing the X and Y component of the electric field. And if the polarized light passes through a medium, the medium can change the polarization properties. So when we have the relation between what is the polarization output is given by E prime, and E is the input polarization state of the beam. We have what the medium does. If you have one medium, that is a Jones matrix of that medium. So if you have multiple media which change the polarization state, then we have to multiply all these Jones matrices to get the effective polarization. These are some of the standard procedures we use. And we do not have always, starlight is not completely polarized. We have partially and unpolarized light coming. In such case, the Jones matrix doesn't work because it works for only a polarized light. But in practice, we have a unpolarized or partially polarized light. And those light characteristics can be described by the Stokes vector, which is basically IQ, UV, 4 parameters. They are also described in terms of basic components of the electric field, Ex and Ey, like this. And basically, any instant light, if you have a retarder plate and a quarter wave plate, something which you can rotate the plane of polarization, we can measure the intensities, and from the intensity, we can measure all these parameters. So basically, Stokes I is a total intensity. Stokes Q corresponds to the difference between the linear polarization at 0 and 90 degrees. And actually, I have not given this equation yet. We can actually express this total intensity as a function of all this, which basically will come out to be this definition. Stokes V is difference between linear polarization, and Stokes U is a difference between linear polarization 45 degree and 135 degree, and Stokes V is a difference between right and left circular polarized light. So the degree of polarization would be basically sum of square of QUV. There are different notations. Some people call S1, S2, S3, and I have written use this parameter. So this will be the degree of polarization. Just like a partially fully polarized light, we have Jones matrix. We have a partially polarized light when it passes through medium or the optical component which can change the polarization state. We get a Muller matrix which maps between the input polarization and the output polarization. If you have many media, many components, it goes like this. These are all the various Muller matrices representing various optical components. Now, these are some of the basic phenomena I describe what is polarization. These are the important things which we need to know in designing optical backend instruments. And also we need to understand the concepts of images, pupils, and beams. So generally, what I have shown is an image formation with a single singlet lens. It's a very simplified picture. At the focal length, you have the image. This is the pupil, and then we usually put in a stop to limit the angular rays coming in. And this is called aperture stop in the pupil plane, primary pupil. And when the image is formed, we call it as a field stop. We select a portion of the image, but that is in angle, we can limit the field basically. And we can use another lens, usually which is used in many of the telescope. We use one or two lenses, just re-image that to an image space. it can be either for reduce the scale or enlarge the scale. And in the image, at the image plane, the object information is coded in the position. As we move from one position to other position in the image plane, we get the as a function of angle in the sky or what is the various intensities of the object. And if you have a point or several point objects where they are located with respect to each other, that can as a function of position we'll know. At the pupil plane, each point has contribution from all the object points. For example, if we have a rays of coming from here, that this particular point can have contribution from rays coming from different directions. So that means different object points contribution is there. Almost all the points object points contribute to the light received at one particular point in the pupil. And the focal ratio is the f number, focal length by the aperture diameter. For example, if we say f30 means f by d equal to 30, where f is the focal length and d is the diameter of the lens. And then usually converging lens means the rays come to a focus like this, they come to a focus. And diverging beams rays fan out from a virtual focus. And collimated beam, all rays coming from one object points are parallel. Okay. Now there is also an aberrations in the system because all the optical elements are not completely perfect. Towards the end of this talk, I will also talk about this optical design principles, how we can design. We'll get to know that it's always good to have an oversized optics because the edges of the optical components are not always perfect. And moreover, any optical component design will have its own limitations. So that will be imperfection in the optical system. It will cause an aberration. So, and major aberration is basically something which tilts the image, which is not a major problem unless you are going for a long exposure image, because tip and tilt will only shift the image in the image plane. Whereas there are different kinds of aberrations, which I'm sure you have, at least those who have done BSc and MSc physics would have gone through in your schools. Just a recap of that. There are two kinds of major aberration: on-axis aberration and off-axis aberration. That is, off-axis means on the axis of the telescope or image plane or slightly away from it. A perfect system, what we have is this is a central spot. The exact focus on either side of the focus spot will remain like this. This means what is shown here is a wavefront, that is a pupil of your telescope, and it is shown as perfectly UN, means it is uniformly flat. It's ideally a flat wavefront. It has no aberration. That's what we expect. For a point source at infinity, the wavefronts are almost planar, flat wavefront. Without, in the absence of the atmosphere, they will be perfectly flat wavefront. And that's we get a perfect image if the optical system is fine. But if there is a defocus, what we would see is that if we go from either side of the focus, image will not increase uniformly. Whereas you will see the pupil plane will look like this. The intensity won't be flat, and the image scaling is the 1 over focal length square. And the spherical, if you have a spherical aberration, this is the image plane will look like this is the actual position. On either side of the position, you will see the image changing like this. And it goes as 1 over f cube. This is the equivalent pupil image if there is a spherical aberration. Now, coma is an off-axis aberration, where if you you look like a comet image, and this will be the equivalent pupil image, where one side you have brightness and other side is slightly dark in terms of the phase distribution. Astigmatism would mean that there are on either side of the focus, image is changing, like this in one direction. If you go from perfect actual, the so-called the focus position, one side the image will not be exactly the same. Unlike the perfect, it will be elliptical in one direction. If you go, it will go to in other plane, it will become expanded in other direction. And field curvature is depending upon the at the center, you may have the same. As you go away from the field center, the image plane, the plane where the image forms is exactly not two-dimensional plane, it's just curve tilted. So these aberrations have to be taken. One has to analyze when you form the optical component. We have to design such that all these aberrations are minimized. Of course, it is not always possible for an entire field of view to minimize this aberration. So depending upon what we can, our requirement, we can sometimes can afford to have very small, if you're interested in very small angular field of view, probably we can ignore this comma, because it is an off-axis aberration. Because for a small angular region, it won't be a big problem. But off-axis, depending on the application, we have to design optic system based taking into this aberration, and corrections also you should make. Generally, in astronomical telescope, at least the ground-based telescope, says what is happening is basically we can describe the pupil function, the telescope aperture, as a complex aperture function, which is some complex amplitude and a phase function. And if d is the diameter of the aperture, and if you have for a given d, lambda z by d, where z is the distance between the pupil plane and the image plane, lambda z will be the size of the diffraction spot, and d is the size of the geometrical spot of the aperture. The ratio of these two is called a Fresnel number. And if Fresnel number is very large, we call it as a near field approximation, Fresnel diffraction place. And if Fresnel number is small, which means f is small, means diffraction effects are larger, because the denominator is larger, so it becomes very small. We have Fraunhofer diffraction in most of astronomical instrumentation. Image is far field to image plane, so Fraunhofer diffraction applies. Basically, the aperture diffracts the light, and the lens or set of mirror system brings that diffractor rays to the focus. So if you look at this, this is the, I mean, I given an arbitrary shaped aperture, but in most of the astronomical telescope, it is a circular aperture. So this is the pupil plane field, and this is the image plane. They are here I've shown it as parallel to each other, and it is known that the image plane electric field, the field in the image plane, is exactly the two-dimensional Fourier transform of the people in field in the pupil plane. And this is so the phenomena of the diffraction can be completely represented by a Fourier transform expression. And what is a point spread function? These are some terminology. If you have a point object, and if you have a telescope of finite size, because you're not telescope as a finite sized aperture, even if it is perfect, the image will not be exactly point, it will spread over certain region. That intensity we call it as a point spread function. For it is a property of the instrument. It's independent of the object itself, because it is how the light for a point star or source, how the light will be distributed in the image plane. That's what the point spread function gives. But in the case of an extended object, where the object is much larger, angular size is much larger, it's not a point source anymore, it is well resolved, then the image formation can be written as the convolution of the object with the point spread function. And these are the typical examples of the point spread function we have. For a circular round aperture of diameter d, we have the airy disk pattern in the central one, airy disk pattern, and this is the point spread function. This is shown, I have shown it here, is a logarithmic scale, and this is physically we can express Bessel function of first order. And if there is an obscured diameter, if most of the astronomical telescopes, as we will see in later, for various reasons, we need to obscure the central portion of the light from the lens. Central portion of the light. So if there is an obscuration, sorry about that. Central portion of then if there is an obscuration, the intensity distribution will be appearing like this. Mathematically, it can be modeled like this. And for rectangular aperture, this is a sinc square function. So these are some way we can, for a known aperture, we can model the intensity distribution at the focal plane. Now, optical transfer function is another terminology, which is basically a Fourier transform of the point spread function. Point spread function is the intensity in the image plane, and if you do the Fourier transform of that intensity, you get the optical. So this is a Fourier transform of the point spread function. And since the point spread function itself can be written as Fourier transform with the aperture distribution and then modulo square, because it is the intensity, right? So this is the people plane distribution. And then we took the Fourier transform, as I told here, this particular chapter. This basically, this is I hope you can see my cursor moving. This is a people plane field, and then we do the Fourier transform to get the image plane field, and then modulo square of that is a point spread function. So this is a point spread function, and then we do the Fourier transform. But we have another theorem which says that if we have a certain relation power spectrum, we can write this as an autocorrelation of the people field. So basically, what optical transfer function mean in an incoherent imaging system is it is an autocorrelation of the field in the people plane. This is amplitude and this is the phase. And in general, this the optical transfer function in general can be a complex function depending upon the phase value. And so we can write it as the product of two functions, modulation transfer function, which is amplitude part, and the phase transfer function, which is the phase part. And if we take the just amplitude part alone, it will appear like this. For an ideal telescope without any obscuration, you get this kind of, this is at a one-dimensional functional normalized angular frequency versus normalized MTF. You get almost the black line. And if you have an obscuration, okay, I think this itself is not, the black line itself is an obscuration of 10%. Okay, if you have more and more obscuration, what you can see that the optical transfer function is changing as a function of spatial frequency. So as you can see, it's basically what it means is that this optical transfer function, when in a convolution relation between the object and the image, the Fourier components of the object will be multiplied by this optical transfer function, which would mean that the optical transfer function by making obscuration in the pupil plane, we can relatively amplify some high frequency component and attenuate the low frequency component. In general, if you have no obscuration, it will be low frequency components will be less attenuated and high frequency components will be more attenuated. But by choosing the optical pupil appropriately, we can have we can change the way the contrast of the image is transferred when the final image from the object to image, and we can relative enhancement of the contrast we can manipulate with this kind of by changing the pupil. This has important application in the field of high resolution imaging, where we can go for closer to the diffraction limit, because generally in the presence of the atmosphere, we will have that something which is closer to the diffraction limit, it will be completely attenuated. As you can see that we can still get a slightly better modulation transfer function by obscuration. So in cases where we are not interested in overall background image, the low frequency component, but we are interested in the presence of a small binary object close to the star, which is a binary star. In the case of, say, extremely large telescope, it could be an exoplanet. We will be able to identify by manipulating the people function. Okay. Now, coming back to the other aspect, optical windows are these are some of the optical components which are used in most of the astronomical instruments. Optical windows are designed to separate environments that differ in composition, pressure, or temperature. They are mostly plane parallel to avoid beam deviation. So the whole purpose is that beam comes, but there is an environmental difference between the outside and the inside. For example, in a CCD sensor, where we want to avoid any contamination of the sensor by direct dust, we can put an optical window which will cover the sensor from direct contact with the environment. But at the same time, you should avoid any beam. You should not avoid any beam. You should not deviate the beam. They will have coatings to maximize transmission, because the aim is just to pass the beam, just to separate the environments. That's all we use. There are different kinds of optical windows are used depending upon the wavelength of interest. Barium fluoride, magnesium fluoride, lithium fluoride, germanium, silicon. So many depends on they have a specific windows where they can be used. So the wavelength range and the mechanical properties and the cost. Sometimes cost is also very effective. For example, sapphire is a very expensive one, but it's a very hard material. It's a very low, high resistant material. It can be used for a wide range of optical wavelength as an optical window, but it's very expensive. But we have to see whether we require such things, whether we can manage with something same with a similar subject. But it is highly resistant to, and it has a chemical resistant against the chemicals. So it is probably good to use this in certain conditions. Generally, all these optical windows, there is a definite ratio that the D is the diameter and the thickness. The thickness, diameter by thickness should be less than square root of the Young's modulus, right, delta P, whereas the delta P is the difference in pressure between the two sides of the where the windows is kept. And lenses. First I started with the optical windows. Basically, optical windows, they are not power beam. They don't do anything to the beam. They just pass through the light. They don't do anything to the light. Whereas lenses do manipulate the light. They bring the parallel beams to focus, or depending upon the lens combination, we can manipulate light, because these are called power optics. They just interact with the light and changes its path as the light travels. And the transparent refract, these are refracting optical elements made of glass or crystals. The material selection is based on the wavelength range in which we want the lenses to be used, and the refract index of the and then the diameter we want to use. Basically, the thick lens equation, F is a function of radius of curvature. This is the radius of curvature. This is one example. You don't have to know the exact details, but just to know these are various terminologies available. That's all I wanted to go. Lenses are usually have coating to maximize transmission, because lenses are refracting elements. They allow the light to pass through and come in. So they should have a maximum transmission and then minimize the reflection, because if the light is reflected, you lose the light. And at the same time, you should have, as they are transmitting light, they should have maximum transmission so that we don't lose enough light. Achromatic lenses minimize the focal length variation of the given range of lambda. When the input beam has a large wavelength, if you have a singlet lens, you may have the different wavelength coming to focus at different position. But if you have achromatic lenses, which they compensate for different, bring almost a given range of focal length, the same focal point. Thermal lenses, or sometimes if when you are using nighttime astronomy, we need to, or even the daytime solar imaging, we need to have the focal length of the lenses to be stable over a range of time. See, the focal length is a function of the temperature change, and if the focal length keep changing, then our image quality will go bad. So we need to keep on refocusing. Instead of that, we can have design the lens which will take care of the small temperature variation and keep the focal length stable, focus stable. Wide angle lenses have several elements to minimize off-axis aberration, because the more if you have a wide field of view, as I already told, off-axis aberrations will come into picture. So in order to minimize this off-axis aberration, we have several correcting elements. So it is used in this. These are something about the lenses. And in addition to the lenses, we also use mirrors. Mostly the mirrors are used, I mean, it depends on the wavelength of interest, whether we use lenses and the mirrors, where we use lens, where we use mirrors. When mirrors are basically reflective optical elements that change the direction of the beam. They don't refract, just reflect it off, and they change the direction of the beam. Common mirror material substrates are glass, aluminum, beryllium, silicon carbide. Coatings decide the reflectivity, because most of the mirrors are coated so that they should have a maximum reflectivity. Unless the lenses should have maximum transmission, the mirrors should have maximum reflection. And one important aspect of mirrors is all optical properties except for reflectivity are independent of lambda. Only the wavelength, the reflectivity will be a function of lambda. The optical dynamics are 2 times more stringent than lenses because. Sorry about that. 2 times more stringent than lenses, because mirrors have a single surface. Because optical lenses, we have your radius of one surface and two surfaces in lenses, whereas mirror you have only one single surface, so that optical tolerances are very stringent. And aspheric surface minimize the aberration, commonly known as conic sections are preferred. For example, you have a parabolic mirror. Most of the telescope primary mirror will be a parabolic mirror. The sphere will have to avoid the spherical aberration. And these are some off-axis. In case of the mirrors, can also be used in off-axis condition to avoid the beam obscuration, because that will increase your light more overall throughput. It will increase. And then coming back to this next one is filters. Optical elements that change the transmissive, reflective, or absorptive properties as a function of wavelength. Say, for example, you have a optical element which will allow the when we say short pass filter, it will allow light below certain wavelength. It is fully transmitting. After that, it will cut down. So the long pass filter is above certain wavelength. It will allow all the wavelengths, and transmission will be very high. And the band pass filter will have a small range of wavelengths through which it will allow the light to pass. See, the exact transmission function may differ. Sometimes it may be exactly flat, or sometimes it may be a Gaussian shape. And dichroic filters are used in non-normal incidents, both the transmission as well as reflection. When you talk about these filters, there are certain things which are very important to take into account. The typical specification involves the central wavelength of the filter. What is the central wavelength? What is the peak transmission? Because transmission is not exactly flat. It is over a wavelength, it is increasing and decreasing. What is the full width of maximum transmission? These are certain characteristics of the filters we need to get. Long pass and fairly broadband filter. There are colored glass filters which can be used, which are in practical use, which are independent of the angle of incidence, temperature, and humidity. And so these are some of the examples. GG495, RG360. Basically, this 495 implies that after 495 nanometers, it is all transmission. Transmission is very high. Below that, it doesn't transmit. Similarly, other examples of transmission filters. And then we also have an interference filter where thin film coatings and color substrate transmit only a certain band of interest. And narrowband interference filters are constructed from a set of fabric cavities. And depending upon the cavities, number of cavities used, the actual transmission can be written analytically. I mean, we can calculate and then verify. This kind of narrowband filters are also used as interference filter for observation. Another thing for mirrors is basically the coating. Mostly we use for normal mirror surface, we have 3 kind of coatings: aluminum, silver, and gold. And what you see here is aluminum, whereas it has a reflectivity of it increases up to 90% at 600 nanometers, but around 800 nanometers, the reflectivity of the aluminum is very low. There is a dip here, and then it increases. So, for example, if you have a optical surface mirror where you are interested in basically at this wavelength region, you are going to lose some photon because reflectivity of the aluminum is relatively poor at this wavelength. So probably if your wavelength of interest is here and you want to observe objects in this wavelength, probably you will go for a silver coating where you don't lose light, because already we are starving with the light. So we should have more reflectance. So we can go for silver coating or gold coating at them, depending on the cost, taking cost into account. So different kinds of materials are used. In addition, these are major reflective coatings, but there are different combinations of coating which are used for a different wavelength regions for all the optical components. And then in addition to this, the filters I mentioned already, there are specific astronomical bandpass filters which are available basically for some the Johnson photometric system, we have UBBRI filter, whose bandwidth the wavelength range are given by this plot. For example, U band is basically from 300 to say roughly 450 nanometer, and this is B, starts from 350 something, goes up to 550. So we have different range of wavelength these filters allow. Basically these help us to identify classify the star. If you have if a star is observed in 2 or 3 bands and you get a maximum brightness in B band, for example a star is observed in B band as well as in V band, and it's having more flux in it appears very bright in B and less bright, you can say that it's a kind of B star. It has a maximum flux in that wavelength. So in that context they are used directly to classify the stars. And there are different kinds of filter systems which are, this is another example of a Thorn-Gunn filters, Thorn-Gunn filters. And this is another filters, Sloan Digital Sky Survey. They have different kind of filter system where you can express this. And we have a Strangen filter. So there are different kind of filter systems are used basically to measure the stellar properties of the stars. And other optical elements in astronomy are basically the prisms. Basically, prisms are glass wedges with apex angle of alpha. I think most of you will be knowing what is a prism is, because that's what we learn in high school about this split low dispersion, the dispersion of the white light by a prism. And usually prisms are used in low resolution spectroscopy where we do not have very high spectral resolution. It is also used as a cross disperser in high resolution spectroscopy to distinguish between different orders. It's called order sorting filter, and used for image rotation in a prisms can still be used for basically rotating the image as is a kind of dome prism where you have it looks like a right angle prism where the top edge is cut. So the input beam is rotated, and as you go outside, you basically get a image rotation by passing them. And prisms are also used in atmospheric dispersion correction, because particularly when you are looking at the planets at a very low altitude, you would generally see that image is smeared with one side looking red and other side looking blue. It's not completely looking at planet. So if you have this is because of the dispersion of the light by the atmosphere. And if we have an instrument to where we have a combination of two prisms which can be rotated on top of each other, we can compensate for the dispersion produced by the atmosphere and get the sharp image. So these are the sum of applications of prisms which are used in astronomy. And angular dispersion of the prism, deviation per as a function of wavelength. These are some formulas, and spectral resolution will be given by lambda over delta lambda. And grisms are basically prisms with a grating on one side. In a collimated beam, image is dispersed without deviation. So if you have a grism where there is no dispersion here, but only as a kind of deviation of various wavelengths. Another dispersing element which are used in astronomy are gratings, gratings are transmitting or reflecting optical element that disperse the light by diffraction on periodic structures. They are typically used in high resolution spectroscopy, and this is the grating equation where D is the period in the grating, and sin alpha and beta are angle of incident, and beta is angle of diffraction. And the angular dispersion will be d beta by d lambda will be, from this you can derive this, and spectral resolution will be m times L, where L is the length of the grating and D is the separation grating. Okay, I think we can skip over the formula, but basically these are some of the elements available. And another thing which are used particularly in measurement of magnetic fields our polarization properties are the polarizers or wave plates. Polarizers produce light with a linear, circular, or elliptical polarization from unpolarized light. Wave plates are retarded delay the phase of one polarization state with respect to an orthogonal state. Linear retarders are by far the most common and used by reference in crystals. And quarter wave plates transform the phase by 90 degrees linear to circular polarization and vice versa. Basically, these are, for example, if you want to measure your input polarization or Stokes vector, you need a retarder plus a polarizer combination to get the effect IQV, the 4 parameters. We also have optical fibers, which are also used in astronomy, basically to transport light from one place to other place. It is a thin, flexible, transparent fiber made of high quality glass or plastic. It has a core clad, and it basically works on the principle of total internal reflection, because the light passing through this will totally internally reflected, and so that the light, there is no loss of light. And the numerical aperture is the maximum acceptance angle and is relative to the critical angle of the angle for total internal reflection. And I think I'll probably skip this bending. Basically, these are some of the things used in astronomy nowadays very frequently. And then now I go to a very major topic in astronomy, which is detectors. Detectors are basically the ability to detect the photons coming from the sky. These are very important astronomical instruments. Modern detectors of electronic devices made of multiple photon sensitive detector elements. There are many detectors. What are the various criteria which we use for astronomical detectors? The quantum efficiency, basically the ability to convert the number of photons coming from the sky to the equivalent number of electrons which we can detect. For 100 photons, if we can get 100 electrons out in our detecting system, then we have a quantum efficiency of 100%. Otherwise, we'll have something. Usually, we will have some 80%, 90%, where we have for every 100 photon, we'll register only some 80%. And then the responsive wavelength range. What is the wavelength range in which we can use this detector? Format of the detector, number of pixels, and then energy resolution. That is, energy resolution is in terms of how many intensity depth we can have. How stable is the detector, and linearity response, and full well capacity, and polarization sensitivity. These are all the properties we consider. Detector are classified in 2 categories. Direct photon detector, directly respond to individual photons. These are photoconductors like CCDs and photodiodes. Thermal detector, which respond to the temperatures. Coherent detector respond, and this is in optical and infrared wavelength. For a radio wavelength, we have a coherent detectors which respond to the electric field strength, not directly to the photons. The sensitive material of conductors is based on either intrinsic and eccentric semiconductor materials. So generally, this diagram gives you a overall view of what is the various kind of detectors used at various wavelength regions, starting from 0.1 micron to up to 1 millimeter. So generally, this is the range. Initially, the photographic plates were used in the past. Nowadays, photographic plates are not used. Now, silicon-based CCD detectors are used almost in this wavelength up to 1 micron. And then if we go to say 1 micron to 10 micron region, mercury cadmium telluride detectors are used, indium antimonide, and these are various materials which are used at different wavelength regions. And these are at a very high. This region is basically visible and near infrared. We have 1 micron to 10 micron. 1 to 5 micron is low infrared. Then we have mid infrared, where we have 8 to 13 micron, and far infrared we will have all kinds of detectors. Most of these detectors are based on this is, for example, at 10 micron to 100 micron, we have hot electron meter, where we sense the photons based on the terminal conducting, and we count the number of photons directly. So there are different kinds of technologies. Basically, I'll be covering only details of these CCDs, which are basically used in visible wavelength region and near infrared. Different kinds of detectors are being used at different wavelengths. Historically, I mean, this is already here. The historical photographic plates have been replaced by solid state devices, as they have provided higher quantum efficiency compared to the photographic plates. We have quantum efficiency more in CCDs. Photoconductors are also being used from X-ray to infrared wavelength, directly respond to individual photons. In a typical photoconductor, silicon germanium, group 4 of the periodic table, gallium arsenide, indium antimonide, these 3 and 5 and cadmium telluride. These are periodic table 2 and 6. In ground state, the whole principle, most of you know already this. The ground state, the valence band is completely filled. In the conduction band, the next higher energy band is unoccupied, but it is separated by energy gap. If a photoconductor absorbs a photon of energy h nu, which is energy gap, an electron can be lifted from valence to conduction band. Once it is in conduction band, electron is only loosely bound, and applying electric field to the photoconductor pixel will drive the electron to a electrode where it can be detected. The amount of collected charge is then proportional to the detected photon flux. This is the basic principle in which we use. But there is a limit cutoff wavelength for common photoconductor material. Germanium arsenide, you have only 0.9. Silicon have a cutoff of 1.1 micron. If anything less than 1.1 micron use, germanium can use slightly above 1.9 micron. Indium antimonide can use up to 5 micron. And generally in astronomy, both visible and near infrared, we use not even in the visible, we use this charge coupled devices are most common detectors in astronomical instruments, visible range. They are based on intrinsic silicon photoconductor collecting photoelectrons in potential wells and work from X-rays to silicon band gap of 1.1 microns. Important characteristics are quantum efficiency, charge data efficiency, complementary to metal. CMOS detectors are similar to CMOS when complementary metal oxide. When I say this is charge coupled device and this is complementary metal oxide semiconductors. They are similar to C series, but the way the charges are read out to individual photoconductor, they are slightly different. The readout process is different. And there are different advantages of CMOS over CCD. This plot gives less expensive. What are the ways CMOS is much better than CCD? Is less expensive to standard semiconductor fabrication, much lower power consumption, faster readout on-chip camera electronics, random access region of interest, higher tolerance and fixed acceleration, higher radiation tolerance. Whereas CCDs also have some advantage compared to CMOS because CCDs have generally a higher quantum efficiency, reaching close to 100%, larger full depth of and large dynamic range, and sub-electron readout with an electron multiplying, which is electron multiplying CCD, and there is a bending of electron, which can reduce the readout noise or increase the signal to noise ratio, because if you bend the 4 electron, you are reading it only once. Whereas CMOS, each and every pixel is read out, so by bending you don't gain. Okay, these are the eccentric and stressed photoconductor. These are used at a longer wavelength. As I mentioned here, this is the wavelength region, mid-infrared, far infrared, say 20 micron to 100 micrometer range. These kind of semiconductors are used. Eccentric stressed photoconductors are used. And again, photodiodes are also used as are based on PN junction, where you have a depletion region between the two junctions, and photon will be absorbed in either P or N-type region as bias voltage drives the resulting photoelectron across the depletion region, creating a photocurrent. Common devices are mercury cadmium telluride arrays, where relative amount of mercury cadmium is varied to tune the cutoff wavelength. So this is they can go up to 1.7 cutoff wavelengths, 1.7 mm. These are the cutoff wavelengths. So and then we also have avalanche photodiodes, which are very if you have somewhere in application where you have to quickly read out, it's better to go for photodiodes, which are very fast readouts. Where you need high temporal resolution, we can use avalanche photodiodes. This is also used in some of the application in adaptive optics. I will come to it later. Now, as I mentioned, these are detectors in optical and infrared region. In radio wavelength, we directly detect electric field. Coherent detector heterodyne receivers are similar to used in sublimeter and radio wavelengths. Unlike direct photon detectors, they respond to the electric field strength and preserve the phase information. So what we have is a signal from the store, and there is a local oscillator. Then you just combine the LED, and then you get the beat frequency, some on different frequency. Then you separate the signal using a mixer, and you amplify. And I just wanted to point out one difference between CMOS and CCD readouts, which is useful. In the CMOS, what in CCDs, what we have is the photon comes, it's an array of pixel elements where each one is a photon comes, you get detected electrons, and they are shifted row wise and then finally read out. So this charge is transferred across a row and then finally read out. Whereas in there are slight variations in this. Basically, during the readout, the potential belts are moved electrons physically step by step along these pixel rows. One readout or not more readout capacitor at the edge of the array. Readout always terminates an exposure. So when charge moving capabilities also enables binning, where charges from several pixels are combined to before the readout. In a frame trans CCD, we can there are different kinds of CCD where frame trans CCD, by we covering one of the CCD with an opaque layer, an image can be read out while the next image is being exposed. Suppose in the application where we should have very high frame rate, we can read one image whereas next image is getting exposed, that we can use frame transfer. Also, EMCCD is an electron multiplying stage before the readout, which multiplies the number of electrons, thereby provides high signal to noise ratio. Some of the application we use EMCCD. Whereas unlike CCD, each pixel in CMOS array contains its own charge to voltage conversion and reset electronics. So each pixel is read out immediately. There is no transfer of charges as it is in the case of CCD. Each pixel can individually be controlled and addressed via row or column selection lines, which allow the definition of complex regions of interest. Okay, CMOS detectors are often include ADC converters, drivers to operate the reversing detector array, and they form the basis for the multiplex. Okay, basically the point here is that there is a difference in the readout mechanism, because of which we can, in one case, we can reduce the readout noise and increase the signal to noise ratio. I think I will skip this. As I mentioned there, when we work at very infrared wavelengths, we also need technology of vacuum. See, for example, if you have a mid-infrared instrument, the gray box here is where the instrument will be located. It will be surrounded by a cooling stage where the temperature, it has to cool to certain detector. Detector is usually at the thermal infrared, the detector temperatures are typically 6 degree Kelvin. In optical and in near infrared, it is close to 80 degree Kelvin detector. And the temperature of the optics temperature is very, they are kept at a very low temperature. So we have a whole instrument inside a DVAR where we have vacuum wall to minimize a transfer of heat transfer. And then there's a heat shield and the cold instrument is sitting inside the DVAR. So all these technologies are required for doing astronomical instrumentation at the infrared region. Now, going to these astronomical telescopes, there are three major kinds of telescope: parabolic, Cassegrain design, and Gregorian design. Whereas you can see, if a parabolic mirror will bring it to the focus, whereas in Cassegrain we have a small hole in the primary. We have the rays come from top and go to the secondary mirror, get reflected and come to Cassegrain focus. This is another type of configuration. It's called Gregorian configuration. Important aspects in telescope is the F number, the focal length, F by D ratio, and focal length, field curvature, instrument location, whether instrument is located in the prime. This is probably would be called, this is the prime focus. Whereas the primary mirror focus, if you have put directly the instrument here, that will be the prime focus instrument. And sometimes we have a Cassegrain focus mirror, or we can put a reflecting surface here, bring the focus to either side to get an azimuth and focus. And then it also telescope people, as I mentioned earlier, the telescope people shape also is very important. Parabolic primary is to avoid spherical aberration. Off-axis coma will be still present. Cassegrain and Gregorian telescope use hyperbolic and elliptical secondary mirrors. These hyperbolic and elliptical secondary mirrors to significantly magnify the image. The Ritchie-Chrétien telescope or aplanatic Gregorian telescope uses slightly hyperbolic and elliptical primaries to simultaneously eliminate the spherical and coma aberration. Enlarge. Basically, there are different kinds of telescopes, we have to choose whatever we require. If we want to a very smaller field of view, and operations will be already smaller. If you have a larger field of view, then you have to get rid of this coma. So depending upon the requirement, we can design our telescope for a given field of view. In most of the telescopes, after the telescope is there, this is basically the telescope. We will have a f ratio f10 or f58, f13, whatever we have. And when we put a backend instrument, we need to put a re-image the telescope focus to the actual focal plane with a combination of lenses. What I have shown is a re-imaging system with a combination of two lenses. Usually they are called collimating lens and camera lens. When there are basically what you can see here, this is the image plane from the telescope, and I have put a lens which is whose focal length is exactly this distance collimated to the image plane. So the rays going on axis, after the collimating lens, they go parallel. Okay. Now, if a ray coming at a different angle to the center, they reach there. After that collimating lens, again these rays coming from that direction are parallel, but they all converge at a position called the conjugate people plane. And this is a people plane conjugate to the primary of the telescope. And then we can use this collimated beam when it goes to another lens. It goes to the brings to the focus. The ratio of the focal length, the camera lens and the collimating lens will decide the magnification. Sometimes it could be demagnified and sometimes it could be magnification. During the tutorial session, we will have some problems using this kind of re-imaging system. And okay, I think there are something called high resolution images. Supposing you are not interested in wide field of view, we are using very small narrow field of view. We can have the design based on from the telescope focus to the instrument. We can have a completely reflective optics, which are the field intrinsic aberration negligible to we can use the parabolic mirrors and often used in off-axis configuration. We can have a diffraction limiter performance. For example, here what I have shown here is the telescope focus. From there I use a off-axis parabola, which is basically collimating the beam. And I have something called the deformable mirror, which we will come to it later. Basically, a deformable mirror is a thin mirror whose surface can be changed to compensate for the wavefront distortions caused by the atmosphere. And then after that, it reflects off, and there is another mirror which brings it to focus. And here I have a beam splitter which will brings the light to the focus, where I can sense the wavefront shape and give the feedback to the deformable mirror, so that at the detector I get a corrected image, which is this kind of fully reflective system will work for a very small field of view when you are interested in very small field of view. And that's what high resolution. Basically, higher the resolution, the field of view will be generally small. And a low resolution, there will be a wide field of view. And probably you have how much time I have now?
10 minutes.
10 minutes.
Yeah.
Probably I'll quickly go through this spectrograph. You must have gone through the astronomical spectrographs 2 days lecture. Basically, a spectrograph instrument where we split the light in terms using the various spectral components. This is a general schematic of a spectrograph, where we have a slit and you have a collimator which collimates the beam and then makes it fall on a dispersing element, which could be grating, which could be a prism or a combination. And then we have the reflected light, the dispersed light are brought to focus with a lens, where we have as a function of distance, the camera have different wavelengths coming in. I think this is one kind of instrument, spectrograph, and then usually the single split spectrographs and natural spectrograph for high resolution we use. And in some cases where we have we can use a combination of grating as well as prism to get the higher dispersion. So in this case, we have a spectrograph where it produces the overlapping spectra. Then from we can take the light, put another prism, which is as a cross disperser. So the spectrum are dispersed in different directions spatially. That is also is possible. There is also the good olden days, the blinds are used. We used to have a slit test spectrograph where we put directly the prism in the objective mirror, and in the image plane you will see the spectra for each and every star. This is a very low resolution spectrograph. And then we have something called the Fourier transform spectrometer, which helps us to the spectral properties of the source. Is basically a Michelson interferometer type, where we have light coming from the star, passes the beam splitter and goes through two arms, and then by moving one of the arms, we just create a path length difference, which will produce the interference pattern. From the interference pattern, we will be able to establish the spectral properties of the source. And then there are when the field of view is very large. Now, modern days there are spectrometers called IFUs, integral field spectrographs, where how it is done, there are different ways. Suppose let us say that this is the field of view we are looking at, and I have made it for simplicity a grid of spaces in the sky, and then each portion can be used to image a slit in the Ising grand slit array, and then we can disperse and get a spectra of each and every region. Or we can use a lenslet plus and then take the output of the lenslet to the fibers and put all of them in a single line, and then get all the 9 spectra like this. Or we can also use an image slicer where the whole image location is split into 3 slices and put one on top of each other, and each one is dispersed, and you get the fringes for each region. So there are different kind of, for a larger field of view, if you have a very large each special element where contiguous but visually small two-dimensional field of view, because not a single object, you have small two-dimensional field of view, we can get the spectrum. I think we have again multi-object spectrometers, and I will just skip that. And then next coming to this is generally in imaging, in astronomy, as I said, there are spectrograph, imaging, and polarimeter, coronagraphs, stuff like that. In seeing limited imaging, we have because of the presence of the atmosphere acts as a big refracting element. You can say that it's a big lens of certain diameter. That is what is going to decide your resolution, and that particular diameter is called the Freyd's parameter, or R0. So in the presence of atmosphere, where whatever may be your telescope diameter, because of the presence of the atmosphere, we get resolution corresponding to lambda over R0, where R0 is a Freyd's parameter. It's called atmospheric coherence length. It can vary from place to place. Typical values in the visible and visible region is roughly about 5 to 10 centimeter. So even if you have 1 meter class telescope, your resolution will be corresponding to that of say 10 centimeter telescope, and that's why we call it seeing limited imaging. And the diffraction limited imaging would mean we remove the effect of the atmosphere and get the resolution corresponding to the diffraction limit, which is lambda over the D, the actual diameter of the telescope. Generally, you see this R0 will be much smaller than D, so this is a very much larger angle. So our resolution will be poor in the ground-based observation. But if you want high resolution, we have special technology to correct and then reach the diffraction limit. There are different technologies, as I mentioned, to get the resolution beyond the diffraction, seeing limit. And basically, they are interferometry, speckle interferometry, aperture masking, speckle masking, Powerman-Save, and long basin interferometry, and adaptive optics imaging. These are the various imaging technologies which will help you to achieve the resolution corresponding to the diffraction limit of the telescope, even though you are operating under the ground-based seeing limit. So generally, as I mentioned in the previous chapter, there is a parameter which characterizes the atmospheric turbulence, which is given by this number. It's called Freyd's parameter. It is given by this expression, where the Cn square h is represents the strength of the atmospheric turbulence. It's basically called refractive index structure constant, but basically it represents, in this integral, represents the strength of the atmospheric turbulence. So the R0 varies to the power lambda power 6 by 5 is proportional to lambda. So higher higher wavelength R naught will be larger, and smaller wavelength R naught will be lower. When larger R naught means we have a good seeing, or the telescope is we are closer to the actual resolution. Smaller R naught would mean we are limited by the thing, we are away from the actual resolution. Ideal case would be when R naught is equal to D, then we'll get a very good imaging. So similar to this R naught, we have something called isoplanetic size, that angular region over which the point spread function will be uniform. That will be an isoplanetic pack. Usually the image formation equations for ground-based telescope is under isoplanetic condition. Now, the last...
Sir, please try to finish in another 2 or 3 minutes so that we have some time for questions.
Okay, so let me try to do it quickly. This the recent days we have a technique called adaptive optics, which helps us to overcome the effect of the atmosphere and produce high resolution diffraction limited imaging. It contains wavefront sensor, which is array of micro lenses in most of the cases, and wavefront corrector, which is basically deformable mirror. And then I think I will skip the whole interferometer part because it will take long. Just a summary that interferometers are another technology which are useful for a very high angular resolution. For example, order of magnitude wise in a 8 meter class, 10 meter class telescope, we can have a resolution corresponding to 10 meter, even if if you use adaptive technology. Whereas if it's two small 2 meter class telescopes, we can, and putting them separately away roughly 100 meters, we can have a resolution corresponding to 100 meter class, which is 1 or 2 milliarc second. So there is a order of magnitude jump in the resolution achieved. So that can be done, and it is done using interferometer. So they have different technology. I will skip all this interferometer stuff. And then I just want to add one more important thing as far as interferometers are concerned. See, in interferometers, what we have is we measure the interference pattern, and then unlike a full field aperture telescope where image formation takes place, in interferometer we compute the image on the computer, and it's then we do what is called image reconstruction, which is based on the measurements putting the telescope at different position as a function of the separation between them. I think see, coronagraphs are, I think the previous lectures you would have been about exoplanets, and coronagraphs are one of the instruments used to detect exoplanets. Basically what we have is we want to find out the faint companion planet in presence of a bright glare of the star. So what we use is in the primary focus, we just block the light from the primary star. So there, whatever it is in orange color light, it comes from the slightly different angular direction. It's a companion planet. That alone is re-imaged, so that by putting a stop here, we remove the glare, and then we are able to get the and on which this coronagraph used on top of adaptive optics will give you ability to detect exoplanets. And then I will just stop another 2-3 minutes by going through these optical design principles, because these are also very important in astronomy. So basically, my major first principle is minimize the number of optical components, because each and every component is going to scatter some amount of light. They are going to lose light. So in the case of stellar astronomy, you are always going to be storing with number of photons. So we should minimize the number of optical components. Additional optical elements increase the design freedom and can improve the theoretical performance, but also add cost and problems such as ghost reflection and scatter light. Second principle is maximum the radius of curvature to reduce aberration, because low radius of curvature will introduce more aberration. And also if you have a more radius of curvature for mirrors, then it will be easy to manufacture and align. Maximize the allowed tolerances, simplify them. So tolerances should be maximized so that manufacturing is easy and designing operational requirements are very fast. And then if you want to, if you put if a particular optical component is introducing aberration, it is better to put it close to the focus so that the aberration effects are minimized. And then if they place the component close to the people, if all the field points should pass through the same part of the component. These are certain principles when we should use one. Now place a component in a collimated beam if all rays from one field point should pass through the component under the same angle of incidence. And finally, I see this point I meant, always you should oversize the optical elements because optical manufacturing quality is always worse at the edge. Okay, now you use geometrical optics approximation to find the ray tracing and get the performance. Generally, ray tracing based on the geometrical optics, and there is no diffraction effect, even though they are practically there, we just ignore them and use only geometrical optic approximation. And then we, at the end, we usually come across something called a spot diagram, which is basically tells how good is an optical design is. And based on the spot diagram at a different field of view, we characterize the design, that this design is good or that particular design is good. Generally, in an optical design approach is not straightforward. We have to go something like back and forth. We should actually go for requirements, and actual requirements should be translated to optical design requirements. And then the first order design should be made with pen and pencil, with pen and paper and pencil. We should make it roughly. And then we should go for a realistic design and optimized design. And then after getting tolerance, we should have a feedback. So there should be a few iterations back and forth before we can finalize any optical design. I think at this, I will stop. There are some concept of stray light detection, but I will probably ignore them. And this is a basic summary. I have covered quite a bit, a large number. Idea is not to just give you a overview of everything, not to details and everything. You can go back and read the references I have given. Basically, we covered optics, basic principle of reflection, refraction, transmission, and polarization. And we also covered some optical components, lens, mirror, filter, prism, grating, wave plates, beam splitters, and optical fibers. An optical component, BIGS, is optical and IR telescope. And also, I think something which I ignored is the interferometer delay due to lack of time. And then astronomical measurements are done using detectors and imaging and spectrometers, spectrographs. I think we covered all of them. So I will stop at this and then take questions if you have.
Okay, thank you, sir, for the really nice talk. So the first question is by Arya. So Arya, please unmute and ask your question.
Yes, so you said that the focal length remains.
Could you please speak a little louder?
Yes, sir. So you said that the focal length is stable for a large temperature range. So how does the focal length depend on temperature?
Yeah, because the F number, depending upon the temperature, the beam, the exact, depending upon the material used, the focal length will change due to temperature. Because the material gets heated up, right? The material through which, and then the optic surface gets heated up, and though its properties change with temperature, and it eventually leads to a small usual temperature changes of the order of microns, 10 micron, 20 micron. And if you have a thermal lens, which you can minimize that effect.
All right, then the next question is by Gopal Chetty Brahma. Gopal, please unmute and ask your question.
Good afternoon, sir. Thank you so much for this wonderful session. So my question is, you might be knowing about gravitational lensing, the bending of light due to heavily massive objects. So my question is, like, how can we go forward and correct the aberrations or any sort of distortions created by gravitational lensing of objects?
Gravitational? No, your question is, so I do understand that gravitational lensing, when there is a massive foreground of object and some light from background object is bent. This is the phenomenon on the sky, but how we are relating to the instrument.
Yes, sir, because due to bending of light, there may be some spherical aberrations going on when we obtain our final image by detectors or telescopes.
See, for a given field of view, before going for the stellar phenomena and correcting that, we just characterize our instrument, make sure that for a given field of view, our instrument is not producing any aberration. Then only look at this stellar. I mean, there is a possibility that you are there is a aberration which is intrinsically there, can be that's what you are telling, that you how will you distinguish. But before going for observation, we should characterize our own instrument. In most of the time in astronomy, if you have a new discovery, it could possibly that it is coming from the defect in the instrument. So we have to characterize our own instrument thoroughly before going for such studies. It's not an easy task, but we should know our instrument perfectly for a given field of view. This is what we'll read. On top of that, if you go and observe, and then we can say it is not coming because of the instrument, but basically actually coming from the the Einstein rings. If you observe, it is coming from the star and in the stellar, not because of the instrument. That we can say.
Okay, so the next question is from YouTube by Chela Rajendra Kumar. How do we find whether light is fully polarized or partially polarized?
By measuring this degree of polarization, as I mentioned, we can measure the Stokes for a partially polarized light. We can measure the 4 Stokes parameter, IQ, UV. What all we need is a retarder as well as a polarizer. As a function of retarder angular offset introduced by retarder and the polarization angle, with a few measurements we can estimate all the IQ, UV parameters for any partially polarized light, and then using this QUV or sum of square of QUV square divided by the total I square root will be a degree of polarization. So that's what we calculate this partially polarized light, whether it is how much degree of polarization we calculate. Is that answering your question?
Okay, it was from YouTube, so I just read the question. The next question is by Jitendra Singh. Jitendra, please unmute and ask your question.
Sir, which type of telescope are more convenient in observation, sir? Sir, there are many types of telescopes, sir. Optical, IIA telescope. Sir, which type of telescope are more convenient for observation, sir?
No, it's a question of what is the scientific requirements we have. For example, now if you have if we want to have a survey telescope where we just want to survey the entire sky, what are various objects, we should have a wide angle field of view. We should probably put we should have only primary mirror, and we should put the instrument to the prime focus. So it's not a correct question. What is convenient? What scientifically we want to achieve? Based on that, we can design the telescope according to scientific requirements. We cannot generalize that this telescope is good, that telescope, because everything has some advantage as well as some disadvantage. So we have to choose the application. What we want to see. For example, any telescope cannot have a very wide field of view. That is a limited field of view for which the performance will be very good. So, which can be 10 arc minute field of view, 5 arc minute field of view. So, and then we have to design the telescope based on the requirement. Then it will fulfill our requirement. Then it is good. So you cannot generalize that which telescope is good for what a priori, unless we know what purpose the telescope is built for, scientific purpose, which is important in like some telescopes, for example, are important. They want to measure the polarization properties, and some telescopes are very, very narrow angle, I mean high resolution imaging alone they do, for which we don't have to worry about many aberration, because very smaller field of view there won't be much aberration if you use parabolic optics reflection. So it depends on what are the science goals. Based on the science goals and the requirements, we design the telescope to meet that requirements and then use.
Okay, so the next question is by Arvind. Arvind, please unmute and ask your question.
Yes, thank you for the opportunity. Can you hear me?
Yes, please go
Yes, I
ahead.
can hear you.
Sir, is adaptive optics technology active in India currently? And I have heard about adaptive optics for the mass system that is that installed there, or is it only proposed?
Wait a minute. So I don't understand the second part of your question. Can you repeat the second part?
Sir, there's a multi-application solar telescope at Udaipur, right?
Yes,
Yes,
yes.
yes. So they are installing adaptive optics there. I have heard about some news like
Yes.
that. So is it installed there, or it's about to do, or already installed?
Yes. Okay. Adaptive optics is, as I mentioned, adaptive optics is a technology which is enables to achieve the diffraction limited resolution in the presence of the Earth's atmosphere. And yes, there are a few institutions where adaptive optic technology is being developed. There is no, for example, for a solar adaptive optic system is already has been developed and demonstrated at the multiple application solar telescope, the MAS telescope at Udaipur in India. And here at IIA also we are developing solar and stellar adaptive optics, but we are not completely there. We have done the partial, the tip tilt adaptive optic system we have demonstrated both for the sun as well as for the stellar object. We are on the way to demonstrate the high order adaptive optic system for the stellar night sky observation for here. Yes, your answer is that yes, the developments are being done. We are not yet there with the full technology in India. But in one place for solar adaptive optics, we do have working system available at the Udaipur.
Okay, so the next question is by Sumit. Sumit, please go ahead.
Thank you for giving me the opportunity. Sir, I have a question. That is, since graphene, sir, am I audible?
Yes.
So since graphene has a very high broadband absorption range, so in these devices that you have mentioned, especially in the CMOS detector, can we use graphene as a material for the betterment of the detection?
Graphene, because these are complementary metal oxide semiconductors. Graphene, I'm not sure. Probably, I don't know. I will just find out myself. I don't know.
Because as graphene as a material, we have found that seen that graphene shows no band gap, so it's like a semi-metal structure. So
okay, but probably it's possible. I am not very sure, but it probably is possible. If you are...
Okay, so the next question is by Sangeeta. Sangeeta, please unmute and ask your question.
Sir, I'm audible.
Yes, you are audible.
Okay, one of my questions are already answered a few minutes ago. My second question is, can we observe a variable star by using more than one telescope at a time?
Yeah, I mean, at a time, you have two telescopes at your, you have freedom to observe it, same star with the two telescope. I don't see any problem with that. I don't understand the question. What do you mean by, if you have variable star and you want to observe it with the two different telescopes?
Yes, sir.
Yeah, as long as you take care of this, the total flux is characterized based on your instrument is well calibrated, then you can get the stars variability alone. Because when you observe the same object with a different instrument and telescope, you should completely calibrate your instrument so that you can get the stellar properties correctly. So in principle, yes, it is possible. If you have access to two telescopes, you can observe.
All right, so there are no more questions. So we will stop this session here and we'll meet after lunch for the next session on hands-on tutorial on Exoplanet by Aritro. So Crispin, over to you.
Yeah, this attendance session will be shared by afternoon tea break time, and it will be open till the session gets over, 5:30 plus. And please fill the form. And tomorrow, that is 15th July, afternoon session around 3:50 p.m. we will be having a photo session. Okay, so please, we want everyone to be present, and we can make a screenshot of all of us. Yeah, that's it. Okay, and the meeting currently I'm closing it up, and it will be open by 2:10 p.m. Okay. Yes. Thank you.